So getting this, this one, make a step lifetime zero or just. But yeah, we watch the if we delay the happens to those. That's
So this one you have so it goes and it goes up. Its temperature goes up.
Yeah, because
up.
Yeah, temperature goes up, it goes up as we expect.
Yeah.
And this simply comes from the whole combination. It's severe, but that's how it works. So it's minus here minus double there, then you have it. Double into the this is positive.
Yeah.
Then we have plus.
Twice.
And then.
I know this formula. Yes.
Well, then we got the big I start doing the Taylor series. Cancels again. Go to the next coordinate, and next coordinate is this one.
That's what I told you when we were swimming.
Yeah.
I need to go beyond.
I recognize that your words concept.
Yeah. And this
And
one.
then third I even said, oh, I am equal to one. But the temperature for the omega, I said, no, how can I go to one so easy? Now there's
This yeah.
yeah, there is this left, but this will cancel by first expansion in one omega.
Because right.
Because it goes up.
Yeah. And then you have.
And then you have to go to the next one, because I have to go to the next one because the other is one. It's even
You're going beyond. Yeah. That's what I expected. Yeah. Yeah. I think just. Yeah.
So I have to go to temperature which is. It's down to omega zero, that's when the Gaussian.
Very good. How are you?
Yes.
Yeah.
Yeah, which means the solution from Ilya can be exactly correct. That's right.
Yeah, sure.
It's the same structure.
It's the same structure. Yeah. So I'll ask whoever is sitting. Okay, and I will try to do the same. And yeah. So okay. So shall we do? We basically ask the whole group to meet. The enforcement break.
Yeah, maybe we'll do that. But
Yeah.
Yeah.
Then you'll have to use number what's in line.
Yeah, exactly. But I'll just say I'll answer questions later and we go through that.
Okay.
Okay.
我个人真是的，
人家是消脂，
认识，
他最后本分。
不是你本科，所以你是在哪个上好？
23年是24年。
对，23年，我现在就是和国内在这个。
对对。
I'm good. I'm not doing this. I learned those theory from several years ago, but I'm almost forget everything. I'm only writing there. Good idea to, we are feeling it further, so I could see.
There you are, touch here. Yep.
For a second.
Oh, yeah, sure.
Questions from people.
So where do I think it? Yeah, yeah. And it's down here?
Okay, perfect. Yes.
And so. The sound is on the top of the right side. They for example, that's the process. Okay. I I thought it was on but we didn't say that the map in the past, like I saw people also they was they're gonna move like a
Okay.
hour. It took about an hour to do the code.
Okay.
But yeah. Yeah, some people. I thought a lot of farmers working maybe.
Okay.
Yeah, it's yeah. So you.
Yeah, and I'll clarify.
So like.
So this 6 months around, we're doing.
Yeah, yeah. Right, but things are it's built up. It's in the bookstores, it's down. Or. Us, no. Or other. I think it's in my arms. Never talked to them. I said I was name. I learned from the left.
Можно, знаешь, что же это? Что же эффективно пускай с освещением, то есть с освещением повторяется. Стопор, сейчас там традиция лучше, чем да, и бесплатно. Если psychotherapy versus spiritual, it's pretty same. Yeah, only the spiritual stuff has like more tradition in words.
Past 9, so why don't we go ahead and get started? Welcome to the third day of this summer school. And we're just gonna get through by another Agterberg engineering.
So before we really get started today, the three lecturers have decided that it's probably a good idea for all of you assigned to homework groups to meet. Because you're going to have to choose amongst yourselves who is going to present the solutions to problems. And so what we've decided is right after my lecture today, I'll go outside and everyone who is in answering my homework will meet, and then Nikolay will do the same, and then Andre will do the same. So at least you have a chance to see who's in your group. And the idea with the homework is you do it collectively. And then in the end, so I'll assign a total of 3 homework problems. The last one I'll introduce today. And so up to, so each homework problem can be presented by a different person. And also, if the person presenting makes errors, I'm not going to hold that person accountable. I'll hold the whole group accountable. So there's no pressure to be the presenter. So any questions about that? So right after this lecture is done, I'll just go out there and anyone who's in my group, come join me. And then Nikolay will do the same and Andre will do the same. And then you can at least see who's in your group and you can see what has been done on homework and even ask questions if there's some things that concern you. Is there anything else I should add? No? Okay. All right. So we're going to keep going, and today's lecture is going to be, in some sense, the most detailed and technical. And I'm going to use a fair amount of group theory from space groups, which I know maybe many of you have not seen. But I am going to introduce you to all the concepts that are needed. And the main reason I do this in the end is to get some matrices I need for writing down tight binding Hamiltonians. Okay, so that is the goal of most of today's lecture. And in the end, you'll see how to derive those matrices and then how to use those to derive the tight binding Hamiltonians. Okay, so let me just review where we were. So last class, we finished the topological classification of nodes using these three key symmetries of the BDG Hamiltonian. So inversion, time reversal, and charge conjugation. These two stabilize the BCS state, and this was always present. And when we looked at that, we understood why there exist nodes that are not required by symmetry. So in the earlier understanding, nodes were required by symmetry, but now we see how they arrive without that. As a bonus, we understood some sort of topological indices that protect these nodes. So that is useful. We also found out that this classification revealed that if we had even parity broken time reversal superconductors, then we don't get the usual line nodes or point nodes that we expect, but rather generically we should get Bogly-Bott Fermi surfaces. So we went and looked at a multi-band model, in particular this J equals 3/2 model, to see if that actually happens. And I showed you pictures that it did happen. And then we tried to give you some idea of where it came from. And in the end, it turned out that there was some interband pairing that happened when we included this, and this interband pairing drove into the usual BDG description some effective magnetic field. So superconductivity created an effective magnetic field that created the Bogly-Bott Fermi surfaces. All right, and through doing all this, I probably gave the impression that all these nodes that we get are protected by topological invariance, but I thought it just useful to emphasize the fact that that's not the case. There are examples of nodes that we don't know a topological invariant for. And in the context of Bogly-Bott Fermi surfaces, I didn't say this yesterday, but I'll point out that these were protected by a Z2 invariant, which came from charge conjugation times inversion symmetry. But if you break inversion symmetry so that this topological invariant no longer exists, because we can't define it, you'll still have Bogly-Bott Fermi surfaces. So those Bogly-Bott Fermi surfaces are just not topologically protected, but they still appear in the theory. And then finally, just to remind you, I told you more specifically what is meant by Blount's theorem. So Blount's theorem says that the best you can do, or the biggest nodes you can get in odd parity superconductors, are point nodes. And that did not come from this topological classification. That topological classification said that odd parity superconductors have no nodes. And so to get the nodes that Blount's even talking about, we needed to add an additional symmetry. And so I said we had to add this mirror symmetry in the z direction. And to understand the origin of Blount's theorem, we looked at the matrices sigma x, sigma y, and sigma z. And that's what we use to define the d vector, or the gap functions for odd parity cases. And we pointed out that these two are odd under this mirror, and this is even under this mirror. And the fact that these two are odd under this mirror allowed us to get around the sort of codimension arguments that guarantee that there are no nodes. So these two can simultaneously vanish on a mirror plane, while this one remains, but now we only have 2 degrees of freedom on a mirror plane, and that means that we can have point nodes on this mirror plane. Okay. All right, but the key point was those Pauli matrices are odd under this symmetry, and those are even under this symmetry. Okay. All right, so then I gave you a few examples of where I'm going to tell you differences, or I have told you where there are differences from the single band picture. And I've showed you this J equals 3/2 Hamiltonian. And so a natural question is, how do we classify the normal Hamiltonians when we have multiple degrees of freedom? And so most of today's lecture will be discussing the form of this HN, the type binding Hamiltonians that show up. And I'm going to focus today on sublattice degrees of freedom. So when we have more than 2 atoms per unit cell, because I think many of you have derived type binding models before, and you've probably worked with orbital degrees of freedom, but it turns out the sublattice degree of freedom is a little bit more tricky than you might have imagined, and you have to take some care in defining these type binding matrices. Okay, so this is where we ended up last class. First, a quick motivation of where we're going, or a quick picture of where we're going. So as I mentioned, I think we have people in the audience who are aware of the little group of a particular K point. It's easy to define, but what we do typically is when we work near a K point or at a high symmetry K point, for example, here at the M point in the case of iron selenium, then we need to define the irreducible representations of this little group. And I'm not going to dwell on that because it's not absolutely critical for deriving our type binding Hamiltonian, but I will touch upon it for people who are more familiar with this and have looked at this in the past. So I'll tell you a little bit about how you get little group representations and how that shows up in particular in this Hamiltonian later on. All right, so I told you in iron selenium at the M point, so the corner of the square Brouwen zone, you have these 2 Fermi surfaces that overlap. And what we want to understand is where these Fermi surfaces come from. And in the iron selenium case, it turns out there are 2 iron per unit cell, and the degrees of freedom that describe these correspond to those 2 iron sublattice sites. Okay. All right, and so we want to understand, how do we derive such a Hamiltonian, and how do we derive it using purely symmetry principles? Right? And so we're going to be deriving, in practice, what we're actually doing is starting from some local picture and deriving band representations, but I'm not going to discuss that again. I'm going to focus on just deriving the type binding Hamiltonian that we're using, and then I'm going to tell you how the band representations come out. And so here, a lot of what we do can be found, the results of which can be found on the Bilbao crystallographic server, and that's a very useful resource for doing any kind of space group analysis. And one module that you can find there, which corresponds closely to the question of what are the band representations coming from the local pictures we describe, is called topological quantum chemistry. And so you can enter a space group, you can enter a Wyckoff position, and you can enter an orbital corresponding to that Wyckoff position, and I'll explain all that as we go. But once you enter that, you can then figure out at every high symmetry point in the momentum in the Brouwen zone, what is the representation generated for that particular orbital. And so we'll get the formula that they use to do this, and I'll show that to you a little bit later on. So here, as I've mentioned, I rely a lot on lecture notes from Jennifer Cano, and so you'll see bits of pieces of those show up as I go on. All right, so let's begin. So I'm going to work with some concrete examples. In particular, the example I'm going to work on is this simple square lattice. All right, so formally, this simple square lattice is known as P4/MMM. I'm going to work in 2 dimensions because the 3rd dimension doesn't add much for us. This is actually labeled as space group 123. And so we're going to have lattice vectors T1 and T2. And then we're going to have all the symmetries of a square here. All right. Oh yeah, and then here's the momentum, the Brouwen zone. We have a gamma point, we have an X point, and have an M point, and I've been talking about the M point in iron selenium. All right, so first we have to identify our space group. But then within a space group, we know that atoms can be arranged differently. And those different arrangements or atoms are labeled by Wyckoff positions. So here's the simplest case in a simple square lattice. In the middle of each lattice site, I have this single, I have one sublattice degree of freedom per site. And then in this case, if I write down a tight binding Hamiltonian for this, it's going to be something like cos kx plus cos ky, and there's going to be no other degrees of freedom, say if I have s orbitals on these sites. Okay? But that's not the case I'll be interested in today, and I'm going to assume many of you have seen tight bindings generated for this kind of example. But I'm going to instead focus on examples where we have a sublattice degree of freedom. And so here is the same lattice, but now I have a sublattice degree of freedom. Formally, I have two sites per lattice, the red and the green. So you can look at each lattice site and you can see there are two of these for each lattice site. And this is labeled Wyckoff position 2F. Okay, 2 just tells you the number of sublattice sites, and then they label them A and then just alphabetically. So F has no particular meaning here. It's just, it's whatever the, I don't know what letter F is, but the 6th or 7th choice coming in. All right. So you can, so I follow the conventions on the Bilbao crystallographic server. And so these two atoms that sit in the unit cell are sitting at sites 0, half and a half, 0. So I can put an origin here. This is one and this is the other. So these are going to be my two fundamental Wyckoff positions. And what we're going to do is we're going to put s orbitals on these, and then I'm going to put a px orbital on this, and we're going to see what are the tight binding Hamiltonians that arrive and how do they look different. And so strictly speaking, I'll be doing a lot of the work for, I'll do the whole job for the s orbital, but for the px orbital here, I won't do everything. I'll do parts of it, but then your homework is to complete it and then see what that Hamiltonian is for the px orbital, the tight binding Hamiltonian. All right, so to define this, then we need a space group. We need to identify which sublattice we have. But then finally, once we have identified a sublattice, we then need to choose which orbitals we define on that sublattice. And so here, the way we do that, okay, well, you'll see in details how we do that in a minute. But here is an example. I mentioned s orbitals on these sites here, and you've all seen a tight binding Hamiltonian for this case here. Here's s orbitals on the two sites I showed you before, the Wyckoff position 2F. And then we can put sort of a px orbital here. But then you can imagine, because this whole thing is square lattice, when I go to this site, the corresponding atom is a py orbital. Now, one thing you'll see from this is you might guess that we need to put both px and py here, but in practice we don't. The Hamiltonian is complete if we put a px here and a py here. And you'll see how that comes about. And you'll get a different decoupled Hamiltonian if we start with py here and px here. So the number of degrees of freedom, even though it looks like it should be more in this Hamiltonian, is the same as in this Hamiltonian. We'll see why in a second. So what we need to do is then define space group, Wyckoff position, and then the orbital on the Wyckoff position to describe our model. And I'm going to explain this last step a little bit more. Well, maybe I'll explain it right now. We're going to introduce the notion of a site symmetry group. So that's the set of symmetries that keep this point invariant. And then this is going to be some point group. So we've all seen point groups like D2H, D4H, etc. And here it's going to turn out that the point group that matters is an orthorhombic D2H point group. And when we say orbital, what we mean is some irreducible representation of that particular point group. And I'll show you examples as we go along. So when I say px orbital, that's going to be the B3U representation of the D2H point group. When I say s orbital, that's the A1G representation of this D3H point group. And once we define that, then from there, we can get every single lattice site by applying appropriate group transformations. And then we can take a Fourier transform to get to our tight binding basis. So that's kind of the general scheme. All right, but to do that, we first have to, well, understand how space group elements work, right? And so here I'm telling you my generic notation for the space group element. So we're going to have an element of the space group. So I'm going to use sometimes capital G, sometimes little g for the whole space group. And sorry for that, but that's how it ends up showing up here. Okay, but this is an element of the space group capital G. It's going to have a rotation part and a translation part. And so the way this acts on some vector r is it rotates the vector r and adds the translation part. Now, these rotations, for all the rotations in the group, they're going to pass through the same origin, right? So any reflection or any rotation axis, they pass through the same origin. And in the Bilbao crystallographic server, we have a common choice for the origin. If the group has inversion symmetry, then the origin sits at that inversion site, okay? And so you can, when there's inversion symmetry, you look for the inversion site, and then you can say that's where all these elements has to pass. And then we have some translation part that follows. Yeah, so these will look different depending on your choice of origin. If I choose a different origin, this combination will look different, but you can move between origins and figure that out. But that's our common choice. All right, and then what's going to be important in some of what I do today is the product of these elements, G1 times G2. So we have rotations, and so the rotation part of that is just P1 times P2. But what is less trivial is the translation part. So here, V1 is the translation part associated with that. V2 is the translation part associated with that. The net translation is V1 plus the rotation of this operating on V2. Okay, so that'll be important, and we have to keep track of that. And the space group that I mentioned, which is this one here, what we're going to be interested in is generating these rotation matrices for 4 particular elements. And the reason we do that is, well, we're going to generate this entire group by these 2 translations times these 4 elements. So any element of the space group is some product of these elements here. And so if we know the rotations if we know how all of these act, then we know every element of the space group coming from products of these, and we can completely define our Hamiltonians. In practice, since we're doing a tight binding basis and we go to Fourier space, the translation parts don't matter. But what does matter are what are the appropriate choices of rotation elements, rotations for these particular symmetry elements. Okay. So just some notation. So for the translation part, I'm going to have translations along X and translations along Y. I'm going to denote these by n comma m. This means n translations along X, m translations along Y. And a shorthand form for that is z squared, because this is a set of integers that is a group under addition. So n1 plus n2 equals n2 plus, well, yeah. So it's a group under addition, but all this means is we have a pair of indices n comma m. And then I'll just point out something else that may sometimes be confusing in the literature. This space group can often be written as a semi-direct product. So it's written as the point group, which is the set of elements that keep the square invariant, times this semi-direct product of this translation part. And I'm not going to define the semi-direct product, but I'm going to tell you what it not is, so you can get an understanding of why we use this notation. So here we can ask, what would happen if this was actually a direct product? Well, then this multiplication between G1 and G2 would look like this. P1, P2, V1 plus V2, and we wouldn't have this action of P1 on this second part here. So it's not a direct product, but almost like a direct product, and so formally it's called a semi-direct product. Okay. But I mean, as long as you know this, you know what you need to know. Okay, and I'll also use this as sometimes the group for translations.
So I didn't understand, when do we use semi-direct product?
Sorry?
When do we use the semi-direct?
Yeah, so all I told you is so I haven't explained the full definition of semi-direct product, but what I can tell you is this multiplication rule does not correspond to a direct product. If it was a direct product, this P1 wouldn't be there. So basically we apply the rotation for each of these parts separately, independently of each other. But here, this transformation depends on this part here. So it's not a direct product, and we call that a semi-direct product. Yeah.
The Z2 is the translation group. Z2 is the translation group.
Yes, yes. Z2 is the translation group, not just shorthand that I use here.
E1, T2 are inequivalent translation.
Sorry, what?
E1 and T2 are inequivalent to different translation.
D1 and
T1 and T2.
yeah, T1 and T2 are this vector and this vector. Yeah. So these are the and we're doing in 2D. So these are the simple translation vectors of the square laps. Okay. All right. So what we're going to do now is build our basis for a tight binding Hamiltonian in a local way. And so the way we do that is we start with one particular lattice site, and we're going to call that lattice site 0. And so here you'll start seeing the notation. I have a basis where we have a lattice site, sublattice site, and then orbital. And so we'll be doing this often. In fact, here you see it exactly: lattice site, sublattice, orbital. But then we first choose this particular case here. So we have a sublattice site, which we'll call Q. And then we find the set of space group elements that keep this sublattice invariant, G sub Q, okay? And this is a point, and so not surprisingly, if we're looking at the set of elements that keep a point unchanged, that must correspond to a point group. And so this set of elements is always isomorphic to a point group. But because I told you about this choice of origin, we don't actually choose the origin here, we choose the origin here. When we write this set of this particular group in terms of the original space group elements, it's going to be the case that these rotations have attached to them some translation parts. And so I'm showing you here the example. Actually, maybe I'll yeah, okay. So this is the example I'll be focusing on throughout. Okay, so here, this is going to be my original lattice sites. And before I go and explain the relationship between this and the space group elements we write down, let me go a little bit further and say, once we've chosen this site, we know it's invariant under this point group. And so we know that we can choose as a local orbital on that site some irreducible representation of that point group. And we're always going to be doing one-dimensional irreducible representations here to make our lives simpler, because I'm not really as worried about the orbital degree of freedom, a little bit worried about it, but not as worried about it. And we're trying to focus on this sublattice degree of freedom. So our life is a lot easier. We can figure out what these irreducible representations are the second I show you the character table. And I'll show you an example in a second. So in our problem, we're going to have this D2H point group. We're going to look at S orbitals and PX orbitals. And then we can ask, well, we have a set of the elements. Actually, maybe now is a good time to show you this G sub Q. All right. So again, we can work with the Bilbao crystallographic server. We can go to the space group. Okay. Looks like I chose the wrong site. Okay. We can choose the space group, and then we can choose the point, and then we can ask what symmetry elements keep that point unchanged. And in the crystallographic server, all those symmetry elements are listed here. This is the three-dimensional rotation corresponding to the rotation part. And this column here is the translation. Okay, so this is the identity rotation followed by no translation. But then if you look here, here we have a twofold rotation about the z-axis. So that flips x and y and not z. But then you can see this is followed by a translation of 1 along y. And the simple reason is because, again, this is our origin. So if I do a rotation around here, this site is going to go, say, maybe here. And then to get it back, we have to translate. Okay, so it's because we have the origin here. And so you can look up these, in Bilbao, go to the Wyckoff position, you can click on the Wyckoff position, and it gives you all the elements that keep the site unchanged. Okay, but what I'm emphasizing is there's some translation parts. it turns out that when we get to the final type banding Hamiltonian, these translation parts are not going to matter. Okay. And then here are the two cases that we're doing. This is the s orbital and this is the px orbital. And so this I got from this. This is a nice page for looking at point group representations. It has a lot of information about them. But the s orbital means just unchanged under all symmetries in this group. Our group is D2H, and so that's going to have 3 orthogonal rotations in 3 different directions, as well as 3 orthogonal mirrors, and then an inversion symmetry. And so I told you we're going to focus on the x orbital. And so we can look at this. One of these are going to be the x, y, and z axes. They're labeled 2, 2 prime, and 2 double prime. Well, when we look, we can see that since we're calling this the x, then this is the direction that doesn't change. So this in this notation is C2x. And then you can look and figure out that this is C2z and C2y. Okay? Yeah, so we'll come back to this. But again, here's the character table, but because all the representations are one-dimensional, this is the full representation. So meaning under a twofold rotation, I either pick up a sign of +1 or -1. So all the representation matrices are just single numbers, and those numbers are +1 or -1 throughout this talk. Okay. All right. Okay. So you see this group, site symmetry group. You see it's isomorphic to this point group, and then we have to choose from this point group an irreducible representation. We're choosing one of these two, and so then we can ask, well, how do the elements of the space group that are not in this little group, what do they do? And then what they do is they, of course, take it away from the site. And so we're going to have elements that go from sublattice 1 to sublattice 2. And in this case, this is going to be this 4-fold rotation C4. But we're also going to have elements that take this to other unit cells. Okay. And so in our problem, we're going to be focusing on this element C4 that takes us from 1 to 2. And so here, there's no translation that follows that because the C4 is here, and that rotates directly like that. All right, so I've told you how to define this particular site. So site 0 by sublattice position 1, orbital I. And now from here, we're going to define the complete basis from this, and we're going to show you how we define that. Okay. Right. But before we do that, we do need a tool from group theory, and that's called coset decomposition. And so it may be the case you haven't seen this before, but so we do need to include it, but it's just a way of breaking up a group into different sets. And so we can take any group, and if we have a subgroup, we can, in some sense, break up this group into subgroups that all contain, into subsets that all contain this group H. And then to do that, we need to have so-called coset representatives. And so we can write this as G1 times H, G2 times H, etc. And then H has maybe, I don't know, N, let's say, yeah, so H has maybe M elements, and then G has N elements. Well, the ratio of N over M tells us the number of these coset representatives. So in our case, we're going to be starting with a point group that's D4H, and we're going to have a subgroup that's D2H, the site symmetry. Or point group can be then broken up into the identity times D2H plus C4 times D2H, right? All right, and so this has broken the group up into 2 sets. And then, in fact, we're not actually interested in the point group itself, but we're interested actually in the space group G. But in our case, the relevant decomposition is we have the this particular space group, DTH semi-direct product with Z2 times the identity plus then C40 times this. But these E and C40 are coset representatives, and they're the elements that relate one sublattice to another. Okay. Okay, so with that, we have the inputs to define our type binding basis. So I mentioned we have a space group, atomic position or sublattice site, and an orbital. And so we know how the orbitals transform under this site symmetry. We can then do a general coset decomposition, and this is the one we'll be focusing on. But there's a finite number of elements here. And in our case, that finite number of elements is 2. And these coset representatives then move between the sublattice sites. Okay. And so, like I said, we have 2 sublattice sites in our problem, so we have 2 coset representatives. And then if we have site symmetry group elements, those rotate between the orbitals. We've talked about that. But now we have the information we need to write down the complete type binding basis. And this is the definition then. So we have site R sublattice alpha orbital I. That's defined as starting with our initial 0 site first sublattice element. We then apply G alpha to get us to the other sublattices in there. And then we translate that to get us to another cell. So using this, we can generate our entire local basis from this. But the important part is the order of these group elements. We first start with our 0 cell, and then we apply our coset representative, which in our case will be this or this. So we either stay here or we go to this. And then to get any other, and to get either this in some other lattice site or this in some other lattice site, we apply this translation. Okay.
Could you explain why it needs to be semi-direct product?
Yeah, okay. So it's not, it's just from the group, the space group product rule, right? So, I mean, yeah, so it doesn't matter too much. All you have to remember is this rule, but it's not a direct product because the group element from here shows up in here. If it was a direct product, you would just get V1 plus V2 here. All right, that's, and I'm not explaining it any further than that. That's one direction. Okay. All right, so in our case then, sublattice 2 will be defined by applying this 4-fold rotation to sublattice 1. Okay. And then in our case, okay, we have s orbitals, so that'll bring an s orbital here to an s orbital here. But since we're using C4, if we start with a px orbital, here we'll get the py orbital being generated by that. Okay, now we're going after the type binding Hamiltonian. And so to do that, we need to understand how does this basis transform under any space group operation. And so here, this is what this slide is explaining. And this is going to be one of the key results that we need. But if we have something that belongs to the site symmetry group, we know how that acts because we know what the representations are and we can look those up. All right, so we know those. But then we have elements that are not in the site symmetry group, some arbitrary space group element. We can ask, how does that act on our basis? And so here, this is just a matter of following definitions. So this is our space group element. And then we operate on site R, sublattice alpha, and then orbital I. And then from that, by definition, we have this translation part. Yeah, this, okay. I realized I forgot to do some examples on the board before I jumped ahead, but I'll do them now in a second. We have this, we have the operator coset representative that takes us to the appropriate sublattice, and then this, and what we're going to try to figure out is how does this operate on this? But before I do that, let me go back to what I skipped. Yeah, so I meant to show you a couple examples of the product rule for space group elements. And this is a good place to introduce some notation. All right, so I'm going back to this slide, and I'm implementing this rule. All right, so here I'm going to apply C4 rotation to an inversion that's followed by a translation of 1, 0. All right, and so when I do the product rule, I get the product of the rotation, C4 times I. This is called S4 usually. But then I need to apply, to get the correct translation part, I need to worry about this P1. So if I do a C4 translation to the vector 1, 0, what do I get?
0, 1.
0, 1, that's right. Okay. All right. And then another rule which we're going to use is what happens when we interchange the order of if we try to move this to the right-hand side of this. Okay, so we have a space group element and a pure translation on the right. Well, you can use the rule to realize that is the same. So you can check that if we do this product and we do this product, we get the same result. And you can check this explicitly. Right? And we will use this later. So we can't simply just commute. This doesn't just commute through, it picks up these rotation points. So this is the rotation times the original vector. Okay. Okay. All right. Okay, so now let's go back to applying the space group element to here. And so this is the definition of this basis element. Here's my space group element. And so now I'm using the rule I just showed you. So I'm interchanging the order of these two, but I need to pick up that rotation part. So that shows up here. And now I'm focusing on how this operates on this original basis state in the 0th cell that I've chosen. And the key point is that we don't know how this operates on this. And we want to figure out how to get something that operates that we know the definition of operating on this. That means we need to get some element of our little group to operate on this. And so what you can do is you can realize that this H times G alpha, so H is some space group element, G alpha is a coset representative. But what that'll do is take us to some sublattice site somewhere else. And we'll call that sublattice site beta. And what we can also do then is we know that if we get to this sublattice site beta from somewhere, we should be able to get to that same site by operating on this. And so to formally use that, we use this, we use our coset decomposition that says that the final site can be found from the original site by applying some element of our coset set, G beta times G. So this is an element of little group, and then followed by some translation. And the important thing that matters here is that we have G beta appearing to the left of this G, because we know how G operates on this, and then G beta will then move us to another sublattice site. And we're going to do a couple examples of this rule because the easiest way to understand it is to do it. Okay, so, but once we do that, we know how G operates on this. That's just defined by the representation. And so we introduce the representation. This translation part we can just include right here right away. G beta takes us to a different sublattice, but we know that's how that's defined. And we also know how this effective translation operates on that. And so we get the original state out by our definition. And we see what the corresponding rotation or this matrix that comes out. And the important point about this matrix is it doesn't depend on R or on this PR plus T, which we're going to call R prime later on. But it doesn't depend on that. It only depends on sublattice. And it also depends, so sublattice meaning we go from site alpha to site beta and orbital. Okay, so this combined element we can write in a larger framework. Yeah, so we're going to use a notation that looks like this. This is what we derived in the last slide. But then if we express it, we can write it as a matrix defined on orbital and sublattice space. But the important property is that this thing does not depend on R or R prime. The final and initial positions it's R independent. And it's going to be this object that shows up in the type binding Hamiltonians when we apply transformations. All right, and so since this is the key object we're after, I'm going to start constructing some of these U's because they're going to define our type binding Hamiltonians. So maybe that was a bit quick, but I'm trying to give you a flavor where all this comes from. Maybe now let's look at some specifics. Okay. So we're going to have our sites 1 and 2. They're going to be related by a fourfold rotation. And we're going to try to figure out what this matrix U is for the generators. Well, we're only going to do it for C40. And then I'm going to tell you the result for the other elements. Okay. All right. Since in the end, this doesn't depend on any translation part, the only thing we need to figure out is how this operates on the sublattice basis. But we already know some things, so we know by definition how this operates. So we defined the second orbital on the second site by this fourfold rotation on the first. So you already know how C4 operates on this. And so the only thing we need to figure out is how does it, I should probably keep it as a space group element. So we need to figure out how does C4 operate on this, okay? And so now we're going to use this coset decomposition because I have not defined how, I haven't defined this yet, but what we know is that if I apply C4 to this, I'm going to end up in sublattice 1, right? So under another fourfold rotation, I'll end up at sublattice 1. And so I need to sorry. I should write this as follows. This is just the definition. Okay. This operating on this is just this squared operating on the original sublattice. So we do end up at sublattice 1. But this is now an element C2Z0. And this thing should be an element of our point group for this particular site, okay? But it's actually not an element of the point group. It does differ by a translation. And you can kind of see that here. If I apply a fourfold rotation, I'll end up here. So I'm not going to end up at the same. So I do C4 twice. I end up here. I don't end up here. So there's going to be a translation part. And so the actual site symmetry group of this doesn't contain this element. Rather, it contains the element, which you can look up in the Bilbao crystallographic server. It contains the element C2Z10, which is, you can see from this picture here. So I need to rewrite this in terms of this site symmetry element times some appropriate translation. So I'm trying to get this times an appropriate translation, and then you can see that that is the following. This I've defined because that is an element of my site symmetry. This is the translation that gets me back to this. Yes. Yep. Right. And so this then becomes E minus 1, 0. And then I'll write this as okay, I'll write this as rho. And this here, I go back to my group table. and I can look it up. So I told you this is my C2Z. And so for the A1G case, it's +1. And for the PX case, it's -1. Done. We've now applied it to the two basis elements. I can now write this as a matrix in the sublattice space. We don't care about this translation part, so these translation parts are irritating to keep track of, but in the final calculation, they end up not really mattering. Yeah?
So then are you saying that the little group contains C2Z10 and not C2Z0?
Yes, and you can
Okay.
see that, okay, yeah, from this picture.
Sure.
Yeah, so C2Z, I'm applying it to here. So C2Z0 is applied at this site, and that brings this, it's not the best place to show it, right? So here, it's because my element is, my C2Z is here. If I apply a C2Z, that brings me to this. To get the site invariant, I need to put that translation back.
What if we were to shift the origin to the center point of the this unit cell?
You mean put it here,
No, above. So like at half. So
like here?
yeah.
Yeah, then these elements would all change. Yeah, so I have to think about it, but you can rewrite everything that way. But the convention is the origin is where inversion sits, and that's where all the rotation and mirrors go through. And so that's our choice. So you have to choose a convention.
It is a different notation for this C2G10. You just call it PC20 or what is PC20?
Where is this?
The last line, the one that you lost.
This thing.
Yeah, what is that?
This is an element of the little group. And then the little group is defined by representations of the little group. This is the irreducible representation for the element C2Z of the little group. So this thing is +1 for S, -1 for PX.
Like that is universal notation as a PC or what?
A universal notation, I mean,
I'm just asking like
What does P mean there?
yes.
oh, this is rho, that's not a P.
Yeah.
That is, so representations are often written in terms of rows, and then they're defined as matrices rho ij. So this is a representation matrix for our group element. But in our case, these are all simply scalar numbers. They're all ±1. So, and it's useful to see how those come in. So I should introduce an ij here, but I've dropped it, so I've been a little bit lazy. Right, but you see that these are all diagonal and just numbers ±1 based on this point group I'm showing here.
And C2G10.
Yeah,
Sorry, C2G0 can be written as product of these two things, E-1, 0 and.
yeah. So you can just use the space group rules I showed you before to check that explicitly. Yeah, I mean, so it's going to be EC2Z, this translation plus this translation, which is 0.
Nice.
Yeah.
So in this context, does it matter if you consider projective representations as opposed to just representation?
So I'm not really going to talk about that. That shows up when I talk about these little group representations. And in these little group representations, many times when people talk about it, they talk about projective representations of the point group. Here, this doesn't enter yet. It's when we go to Fourier space and we look at the little groups at each K point. But then indeed, a common way of discussing this is in terms of projective representations of the point group.
So do you end up finding more UREPs by?
Yes, in fact, yes, so you do. And we'll get a little bit into that, but I don't think I have the time to go through everything, but you'll see, I'm just trying to give you a flavor so you understand, yeah, what's involved. Okay. All right, so we've applied this element C4 to this. And so now I can tell you what this matrix is in matrix form, where the basis here is sublattice. So it's going to be 0, 0, 1. That's this one here. And then here, okay. Okay. all right, I'll stick to rho. And so rho of C2Z. Right, and that's this element here. And again, I don't care about the translation part. So that's my matrix, and you can see it's different for the s and p orbitals. So for s, this is the tau x matrix, because this is 1, 1. And for p, this is minus I tau y. So in sublattice space, we get two different representations because this irreducible representation element is different for the s and px orbitals. Okay. So this, by the way, is telling you that the tight binding Hamiltonians in the end are going to be different. Yeah.
Any reason we are just restricted to 1D representations?
Why I'm doing it for simplicity, really. I mean, in practice, you can generalize this more, but the focus is the sublattice degree of freedom today, not the orbital degree of freedom. And you want to see how it is intertwined with the orbital degree of freedom, but you can see some of that with one-dimensional choices, and that's what this is showing. All right. Yeah.
Can you explain why we have -1 for the p orbital, like using the figure that you had before?
Oh, yeah. So yeah, so the p orbital is this plus minus, and then a C2Z is a twofold rotation around here. So I do a twofold rotation around here. I take the vector and I rotate it around. I come like this. I've switched the sign of the orientation of the vector. That's the -1.
So I can understand this -1 as the phase difference between the p orbitals that before and after your rotation.
Yes. Yeah, you can. Yeah, that's.
Thank you.
But actually, this is the definition, right? So it's useful to have the picture, but it's defined by that. All right. So what I've done then is I've derived this, the matrix U for this particular two sets of orbitals. Yeah, these two orbitals. Yeah.
So that matrix, that 2 × 2 matrix, you have 1 there and something that depends on the alpha, right? So is it because of particular choice you have made that this? So the 1 is coming from when you apply C4 on the phi1 alpha, right?
Yes. The one, yeah, the one here. That's right. That's the one. That's this.
That part doesn't depend on alpha, you're saying, but the other one depends on alpha.
Yeah, that's this part here.
So is that because of some choice you have made in your in defining your unit cell and all these things? That's why
I mean, it is closely tied to all the definitions I've introduced. So it comes from the definitions.
Yeah.
Okay. Okay, so this is the only example I'm going to do. And so it's good that you're asking lots of questions about it. Do you understand it? Yeah.
So the U of H that we have, that is basically all operations which map one lattice side to the other, or one sublattice to the other.
So the U.
Yeah, so we did an example of C40.
Yes.
So
C.
what other symmetry operations can, so these are set of operations which map sublattice 1 to sublattice 2.
Yes. Okay. Yeah. So what we're interested in is actually all the generators of the space group. And there's 4 such generators, 4-fold rotation, inversion, and a couple mirrors. Some of them will map the site to itself, and some will map between the sites. So I only show you this example because I wanted to show you how this appears here and how it's different. I'm going to write down now the matrix for the other generators.
But how do we, for a given space group, how do we know the generators? Because I mean, we don't see them in the character table.
No.
So how do we know the generators for?
I mean, you can look them up. So yeah, you can look them up. So they exist on the Bilbao crystallographic server. I mean, from the example I showed, it should be clear that you can generate every element of the group from these 2 translations and these 4 rotations, right? Yeah.
Can you explain again how you generate the matrix there?
This matrix? Yeah, so what I've done is I've applied C4 to the first, my initial site, right? And that gives me this. That was the definition. So that's the number 1 that appears here. So if I apply this matrix to this, to a vector where this is 1, 0, I'll get 0, 1, right? And then similarly, if I apply it to the second site, then I pick up this element here. I don't care about the translation part. And so I'm going to get, if I apply this to a vector 0, 1, then I'm going to get 1, 0 times this vector rho of C2Z. Okay?
Yeah, thank you.
Okay. So I've given one example. And so now I can write down all the matrices, and we're going to need those a little bit later on. But and I have the answers written down here. And you can check these for yourselves. And for the homework question, you can just take these as given. So this is the answer for both the s and p orbitals. Yeah, so you can see some of these are an identity matrix times a number, this one and this one. And then this one and this one are different for the s and the p orbitals. So in the p orbital, this picks up a -1, mirror on the p orbital flips px to minus px. But around the y mirror, it doesn't do that, so it picks up a +1. So this is going to be tau z for the p orbital and tau 0 for the s orbital. All right. Okay, so we've implemented this rule. I'm going to try to get to the type binding maybe a little bit faster than I should, but I'm going to assume you guys have seen some type binding. And I'm going to highlight the key points here. So we know we can write down a type binding Hamiltonian, and we can look at the hopping between some site r prime and then some site r prime plus r, and we can have it from one sublattice or between the same sublattice or between different sublattices. But we know that what really matters is not the r prime here, but the vector r. And so we know we have a translational symmetry in our type binding Hamiltonian, and we can account for that translational symmetry by doing a Fourier transform. And so the second important detail in this is the choice of Fourier transform we make. And so here is our Fourier transform choice. And the important thing to keep track of is we're on sublattice alpha. We're going to have this vector component r sub alpha. So there are other choices for this Fourier transform where we can ignore this. But it turns out with this particular choice, these symmetry elements can be used explicitly as written down. But if we don't make that choice, if we choose something where this doesn't show up, this won't work. Okay, so this choice is important here. Yeah, and then once we have this Fourier transform, we can write down our type binding Hamiltonian in K space as a matrix between these particular states. And so that's written in this form here. So that's just an inner product of this on either side of here. And then we pick up, depending if we're coupling elements between sublattice 1 and 2, we'll pick up these vectors R1 and R2. So I mentioned this choice is important because it has one awkward feature, and that's something we're going to have to keep track of. It's awkward because typically when we write down a Hamiltonian, that's a function of K, we want that to be invariant under the reciprocal lattice. So we want h of k to equal h of k plus reciprocal lattice vector. But this Hamiltonian doesn't satisfy that because these are fractions of the unit cell. And so we're going to pick up some phase factors from this. So this Hamiltonian, the off-diagonal elements are not periodic in the unit cell, but the diagonal elements are periodic in the unit cell. And that's going to show up later on, but it's an important constraint. And the way we capture that is we define this diagonal matrix. And this is just for convenience, but it's basically accounting for this phase factor. And then we say the periodicity of the Hamiltonian under a reciprocal lattice vector. Well, just following this rule here, we pick up this phase factor times h, and this phase factor is not necessarily 1 because, again, these are not lattice vectors, but fractions of lattice vectors. But we can rewrite this as as a matrix element of this matrix V times H times V. Okay. And sometimes in some places, this is called the gauge matrix. But it is, so in practice, what happens for the choices we make, this factor is either +1 or -1. -1 if we're connecting the two sublattices, and +1 if we're not. Okay. All right, so why do we do that? Well, I've already hinted at why we do that, because we'll be able to use these matrices to define the type binding Hamiltonian explicitly. But just to show you, give you a feeling of where this comes from. So here I'm looking at our lattice again, and I'm now using the gauge choice we made to write down the type binding Hamiltonian, okay? So in the gauge choice we made, I can write the Hamiltonian as this matrix in the sublattice space, just like I've been talking about here. And it has this nice factor cos kx over 2 times cos ky over 2. But I can also say, let's choose a gauge or a choice where I don't include these r sub alphas. I just set all these to 0. That's an allowed choice. And I can ask, what does my type binding look like with that choice? And so here I've written down the hopping from site 1 to 2, and this is the matrix element for that. Okay, and you can see where this comes from because we have 4 hoppings from this site to this site, so we're going to have 4 terms. Here it nicely simplifies through the algebra, but this thing doesn't look so nice. And you can see that in practice, this has real and imaginary parts. And since our Hamiltonian has to be Hermitian, this means that the matrix for this is going to involve not just tau x, but also tau y. And so it's hard to say we can associate anything nice with tau x in this particular basis here. So you start to see why this choice might be better for defining symmetries of these operators as opposed to this choice here. Okay. Yeah.
Then, the metrics that you wrote over there.
Yeah, here.
There is a consistent with the gauge, considering the relative phase. But then, if I try to convert those matrices to the another gauge, so it's to the which doesn't count the relative phase.
Yeah.
Then I think
It
just a
does.
little bit. Yeah, I know that the gauge matrix is basically like the gauge transformation between gauge 1 and the gauge 2 in the phase space. Like those are real space.
Yeah, this is correctly defined in real space.
Yes.
And so what we're going to worry about is how these real space definitions change our K-space Hamiltonian. Yeah, and so we're going to get to that in a second, but I'll give you the upshot. These show up nicely in this particular gauge choice, but they will not show up nicely here, even though I won't answer that. But the way to do the problem is write down the Hamiltonian in this basis, and then you can figure out the gauge transformation that brings you from this to this, and then you can get a periodic Hamiltonian from that if you need it. Periodic in reciprocal lattice. Okay, but this starts to tell you why our choice is useful, because this is certainly much nicer than this, right? Oh yeah, and then here, notice that we don't have these, we don't have a reciprocal lattice vector keeping h unchanged. So if I add a reciprocal lattice vector of 2 pi here, I pick up a phase factor of pi, so I pick up a minus sign. So here, this is clearly not invariant under the reciprocal lattice vector. All right. So, yeah,
So this is a symmorphic group, right, before MMM.
yeah.
How can we, in principle, we can get rid of all these translations?
Yeah, yeah, so you do, and so I'm just going to tell you that you do get rid of all the translation parts in the symmorphic group, and even in the non-symmorphic case, you'll get rid of the translation parts. But I'm going a little slower than I wanted, so I'm going to tell you the answer now, and I'm going to leave 2 slides of algebra that you can work through to see how you understand to get to that answer. But so just so that we can get to somewhere where we can do examples of this. All right. So I told you how we told you the symmetry transformation for these real space cases. So for the real space basis, and we've introduced the Fourier transform. We want to understand how we transform the k-space choices. We want to understand how G operates on this, and we can define that. And the key thing I'm going to point out is if you go through the algebra, here's your final result. You get a block state that's at a rotated k vector. You pick up this matrix that I've been writing down before, and then because of the translation part in this space group element, we pick up a phase factor e to the minus ipk dot v. But go through this algebra. There's 2 main steps to sort through. One is you need to use the fact that the inner product of 2 vectors is unchanged when you rotate the 2 vectors by the same amount. So that's this step here. And then the other issue is you need to relate this vector to this particular choice of r prime so we can define the Fourier transform on this r prime. And I tried to give you a hint to how that happens here. But once you do that, you can see this result. But again, this is what we're keeping track of. This phase factor is not going to matter that much. Point is, we know how we can transform the Fourier basis, and you can derive it here with the group element. All right, so then we can now apply it to the Hamiltonian. And again, the algebra is here, and this is something that's not even so straightforward to explain. This is something you do need to work through to understand. But what matters, again, is the final result. And so here's the final result that I've been hinting at. So we have our we're applying our group element, like for example, this C4, and this UG is this matrix here explicitly. What we find is that here exactly this matrix UG shows up on both sides, and then we transform K to the rotated K from the vector, from the space group element. So our space group element has a rotation times a translation. That rotation clearly should rotate. Say if we start K here, we apply C4, we should end up at a K over here. So that's what this says. But then in addition, we have to keep track of this matrix here. So the key point is we have
H,
sorry,
very quickly. So what is HP?
H what?
What P here means? You apply UG and then HP and then minus 1.
Yeah. So our so here our H, little h, what do we call it? G. Yeah, G is PV.
Yeah.
Yeah. So P is
Okay.
the inverse of the rotation element of that space group element. Yeah, so this is the key result we're going to use. And then we're going to use this and also the non-periodicity in the reciprocal lattice to write down the type binding Hamiltonians. You had a question or?
Yeah, so this is the constraint equation that you need on the elements of H.
Yes,
And using this, you can sort of constrain the space. Okay.
exactly. Yeah, that's right. Okay, so yeah, the rest of this is going to the blackboard and writing down the form of the type binding matrix, which it looks like I'm not going to finish today, but at least you start to see what the 2 rules are and how we can do it. And then I want to use the there we go. And then I want to turn off the presentation. Mm. Yeah, I, if I hit shutdown, it'll shut it off, but okay, I'll just do that. All right, perfect. Okay. All right. So now let's construct the tight binding Hamiltonian. And what we've derived maybe is slightly too quickly, but we have two rules. So we have periodicity on the reciprocal lattice. We pick up this phase factor. So if R alpha and R beta are different, so we're looking at inter-sublattice hopping, this phase factor will matter. And you've already seen that show up. And then the second rule we have oh, thank you. Is when we apply a group transformation with a rotation part P, then the Hamiltonian must transform as follows. Okay. All right, and we're looking at this problem again. And now we're going to focus on the s orbital case. So we have two sublattices. And so now we know in this notation that most of our rotation elements are just a simple diagonal polymatrix, but then our C4 is interchanging the two sublattice sites. Okay, so it's a tau x. All right. Now, we also know, so here I'm not including spin orbit coupling. Without spin orbit coupling, we only have two states. And so our Hamiltonian needs to be some linear combination of all four polymatrices in those two states. Tau 0, tau x, tau y, and tau z. And what we need to figure out are what are these functions. And to do that, let me start with an actual simpler problem. What I'm going to do now is, since I know what all the elements, these matrices UG are, I can assign symmetry labels to these polymatrices. Right, and I'll show you what I mean by that. So here, okay. So what I'm trying to figure out now is each of these polymatrices, what symmetry does it belong to, right? And I know what these matrices are. So tau 0 commutes with everything. And so tau 0 is going to be unchanged by all symmetry matrices. So my transformation is basically UG, tau I, UG, okay, permission conjugate. And so I'm applying this to each of these, and that's going to allow me to assign a symmetry to each of these matrices. So tau x, well, the only non-trivial matrix here is tau x. Everything else is tau 0. Tau x commutes with all of these as well. So tau x is also 1 across the board. But now we see that tau y anti-commutes with tau x. And so we're going to pick up a -1 here, a 1 -1 here. Yeah, and I guess everything else is an identity matrix, so makes their lives easier. Now, I've only given you a partial list of all the characters, but of course, these are all the elements that generate the group, so I can get all the other characters by multiplying them out. And so now I can characterize these as elements of D4H, or as irreducible representations of D4H. And so when I do that, I get A1G A1G, and then B1G, B1G, and in my notation, this has the same symmetry as cosine kx minus cosine ky. Okay. And so now I've assigned symmetry to all these matrices. And so now when I look at this Hamiltonian, I know the symmetries of these. I know how this transform, it just gets rotated to a different k. But those rotations to a different k, I can also ascribe to functions that have these kinds of symmetries. And so the constraint I'm going to pose on the Hamiltonian is that it's an invariant under all these transformations. So for example, if I have tau 0 here, tau 0 is unchanged by all rotations. The function of k that shows up here must also be unchanged by all rotations. And so f0 of k from this, imposing all the rules we have, the simplest form is some cosine kx plus cosine ky. This is unchanged under all rotations, as is this. So this is an invariant that shows up, and we can include it. This also satisfies that the diagonal elements are periodic under the reciprocal lattice, and so this shows up. We also have a tau x term. It has the same, it's the same symmetry, so it must be unchanged under all rotations. But now we have to satisfy this constraint that we pick up a minus sign for reciprocal lattice vectors 0, 2 pi, and 2 pi 0. And we've already seen this because I wrote it out explicitly. This is cos kx2, cos ky over 2. And so this is invariant under all rotations, and it also is consistent with the fact that we need to pick up these factors of -1. Okay? And so then we can say, we can also work out what tau z is. Sorry, fz. Now we have to include the fact that fc doesn't belong to the identity representation. Tau z belongs to the cos kx minus cos ky type representation. So maybe you guys can tell me what is the simplest functional form for this. So tau z has to be periodic in the reciprocal lattice. So it's not going to have these half showing up. It's going to be integral multiples of kx and ky. Well, what do you think this function could be? Yeah, exactly. Cos kx minus cos ky. All right. I'm probably running close to the end here.
2 minutes.
2 minutes. Okay, so there's one subtlety I haven't. So we're almost done, actually, for this first part. So we've almost written down the type binding Hamiltonian. And so you can start the homework question. So the homework question is repeat this for the px orbitals, right? And it's in the notes, in the slides. But what I'll say is we have to figure out tau y. But tau y has one feature which is important. I haven't talked at all about time reversal symmetry in this problem. But since we're talking about orbital degrees of freedom that are real orbitals, time reversal is very easy to represent here. Time reversal is just a complex conjugation operator. The I sigma y doesn't appear because I haven't worried about spin. So it's just this complex conjugation operator. But because of that, my operator tau y is a purely imaginary matrix. This matrix is odd under time reversal, right? And so a consequence of the fact that this is odd under time reversal actually means that tau y is not allowed to show up in our Hamiltonian. I'll explain that in more detail next class. But now we have the type binding Hamiltonian here. We know that only 3 of these show up, 0, x, and z. Tau y doesn't show up, and that's our type binding Hamiltonian without spin orbit. So next class, I'll add the spin orbit to it, and then you'll see how that's included. All right, so we'll stop there for today.
Can it show up with a I? Can tau y show up with an additional I outside? So I tau y?
No. So yeah, the Hamiltonian, oh yeah. So can tau y show up with an additional factor of I? And I should have spelled this out, but the Hamiltonian has to be Hermitian. And so these taus are chosen to be Hermitian. And that also implies that all these functions f are real, right? So all these functions f must be real functions, and so it cannot show up. That would be, yeah, that's an anti-Hermitian term in the Hamiltonian.
Can you explain once again why your fx has that form from this character table?
So first, fx must belong to the A1G representation. So whatever I multiply it by, it must be invariant under all rotations. This is invariant under all the rotations. So like C4 flips Kx and Ky loosely because we don't worry about the sign. All mirrors keep this invariant. So this is invariant under all point group rotations, so that's fine. The one thing I didn't go over as carefully is why is it Kx over 2? Why is it Ky over 2? And I hinted at the fact that that's a consequence of this here. So this phase factor that shows up, the two sites differ by a half-half translation. And that half-half translation, if we have a reciprocal lattice vector whose inner product with that half-half translation gives a phase factor of -1, that has to show up here. So for g equals 2 pi 0 dot a half-half, that gives me a factor of pi, that's a -1. So I need to have kx over 2, but it also needs to be true for ky as well. So ky over 2. I mean, so I also derived it explicitly already when I said, look at how this choice of basis gives a nice tight binding Hamiltonian.
It's not coming from the rotation part, it's coming from the translation part.
Yeah, these 1/2s come from the translation and the constraint that I need to satisfy this. Yeah. Yeah.
So, fractional coordinates convention, unitary matrix will be momentum independent.
Yes.
But in some other convention, it can be.
Yes. Yes, exactly. Yeah, so the question was, in this choice, the matrices that show up here are going to be momentum independent, but if we chosen another particular Fourier transform choice, these matrices can be momentum dependent. And so that's what makes our life a lot easier in this case.
So conceptually, can I understand this procedure as doing like kind of like doing Wigner's classification, but on each sublattice?
Okay, I have to think about that. So the question was, can I understand this classification as doing a Wigner classification on each sublattice? I think that's something you and I should discuss because I have to understand more specifically what you mean by the Wigner classification. So, yeah.
So in the use C4 case, you got 1 and then row C to Z, the off-diagonal terms, and then depending on which irrep we have, we look at the C to Z from the character table. But when I looked at the D2H character table that you were showing, I could not see the mirror operator in the character table. It had sigma V, sigma D, and sigma.
Yeah, that's notation.
How do we get these numbers?
Yeah, okay. Okay, so when I talked, there's a C2 prime, and a C2 double prime.
Yeah.
And I said C2 is C2Z, and I can't remember if it was C2 prime was C2X and C2, but so on. And you can look at the character table itself because you know that under twofold rotation on the x-axis, x is unchanged and y and z change sign. So you can say that must be x. Similarly, for the mirror parts, you get a sigma h, a sigma v, and a sigma d. You can do the same thing. So x changes sign under mirror in the x direction, so you can identify the x.
So actually, I have a question about the summary you were making of yesterday. So when you break inversion and the volume of Fermi surface is not topologically protected, so it's still not any small perturbation can gap it out partially.
Yeah, I mean, this is so you're asking kind of yeah. So the topological protection guarantees that no perturbation subject to the symmetries we've included can gap it out. But now we have no topological protection, but you find in practice they're still there. So I haven't seen a perturbation that actually gaps it out in practice, but in principle, it could happen.
Here you consider only like tunneling up to the nearest neighbor, right? Not beyond that.
Yeah, so the question was, do I only consider nearest neighbor? Actually, the philosophy is simpler than that. What we want to do is we want to make sure we include all operators allowed by symmetry. And so once I can write down that operator from some hopping term, I include it. I stop at the nearest hopping that allows that term to be non-zero. So in this particular problem, this is sublattice hopping between one side and another. And then these are second nearest neighbor hoppings, but also is this. And that's enough to write down all the terms. But you can imagine other problems where you need to go to further range hoppings, for example, to write something like this down. And you can do it, but I always truncate at the smallest hopping, because then we have all the operators in the theory allowed by symmetry. And so we're not adding a lot of other information by adding these other terms. I mean, it adds something, but it's not critical. So as long as we have all the non-zero terms included, it's enough. And you can extend this, right? We can keep adding other terms. We can add cosine 2kx plus cosine 2ky. You can add cosine kx times cosine ky. So you can make these as long as you want.
Again, it's not periodic in the balloon zone. So if you compute sums over momentum, do you need to extend the range of K so it's periodic again, or how do you do that in practice?
No, well, the eigenstates will be periodic.
Okay.
Yeah. No, the eigenvalues will be periodic. And so when you compute the bands, you will have periodic bands.
More questions? All right, if not, I think now we're going to meet in these, three groups. So I think, Agterberg is going to meet with their group, and then the other two professors will gather their remaining groups.
These sections. You sign up for my group here.
Spent 3 hours yesterday computing the polarization bubble.
Okay.
But if you are concerned that you're using.
So for the multiple.
Oh, yeah. Just
So first of all, the problem should be online. So I assume it's already online. And the idea is that you don't work alone, you work in the group. The group organizer. Help you. Want to be group organizer, raise your hands. 3 people, that's all I need. Don't be shy. Your task will be just to collect everyone in one point and just do something together. You can do it. Good, good. You need another one. Okay, then great. So basically, what I want you to do first is to prove actually something straightforward. That's a regular function.
Questions on this?
My question is large angular momentum component. Let's call it Fourier components. then it will be exponentially small.
The smallest group?
I don't know.
And
I think we have about 24. There's never a way to
But basically, I guess the easiest way to prove it is function cosine theta and expand this Taylor.
Yeah, sure, yeah, sure.
And then figure out which component of Taylor series you will need to obtain non-zero result. Yeah, so this is number one. Number two is basically to calculate polarization bubble in 2 dimensions for K4 dispersion, static. And then see whether it has singularities. The only singularities that can happen is close. Right? So the way to find singularity, and then with this singularity, you can again calculate the angular component.
So let's make tomorrow.
This is theoretical. You go to large angular component and you will find that there should be power law singularity instead of exponential. But and this can be done for arbitrary interaction because it's only small combination of momenta which contribute to singularity. But the second part is in some sense more simple but more
Maybe I will share.
take Hubbard interaction. You don't expand anything.
How did we
Just take Hubbard interaction, which you know that Hubbard interaction has zero in all angular momentum components except for L. So you start with zero.
The high frequency.
Like delta equals integral gamma.
Calculate these 4 diagrams. See what you get.
Momentum first.
They contain polarization bubbles, but the trick is, and I will say this tomorrow. There are polarization bubbles as a function of G plus P and polarization bubbles.
Integrate the momentum, and then you get only the frequency result gets it. Right. So after integrating on the gap,
So
you get
then for Hubbard interaction, maybe even numerically, calculate just coefficients.
Tomorrow we
Yeah. Then we're not talking about singularity near K, I'm just talking about the whole expression. And see whether you get attraction. And I pretty much presume that you will get attraction in
Yes. Yeah.
After all
what
the
channels.
talks, I generally.
And then see where which
Okay.
Yeah, we will have more energy.
Yeah, same time tomorrow.
This is a collective process, so just compare
hopefully it
results,
has been
try
each
to
other.
see whether the results are. I mean, that it would be great if every one of you will calculate polarization bubbles and will be able to analyze them. But just compare the results and see what you get. I'm sure you will get the results.
I will give my
This
notebook.
station we can do that. So I'm not sure that you will get attraction, for example. More likely you will.
Okay, this is not a continuation of the story. The first 2 lectures are completely overclosed. No more discussion. Yeah, actually, some of you probably understood Daniel correctly. The group which was supposed to do my homework was supposed to meet after my talk. And that's why probably it was a little bit small because other people simply went eating. So if you want, you can gather again just to see who you are. So you decide how to present. Otherwise, kind of, it's self-organization, but we simply wanted you to see who is in the group. So you can talk to each other and decide the rest. My lecture number 3 is a little bit strange in the following sense. It's in the style of Einstein was wrong. You say, okay, yeah, who wants to, to listen that Einstein is wrong? Not published, not even the draft of the paper is written. And some of the things I'm going to say contradict everything you can read in the standard textbook on Migdal-Ashberg theory. And I'll try to explain why, because almost any book will start with something as simple as possible, as natural as possible, this parabolic dispersion relation for electrons, plus electron phonon coupling, which is purely local, don't even bother about momentum dependence, don't worry much about whether the phonon spectrum has any dependence, simplify every single detail to the bare bone, and just do the calculation. And that's what I know. Our favorite book, for example, in the Soviet Union, Abrikosov, Garkov, and Zelashinsky is doing. And I will try to argue, okay, well, when do you actually use parabolic dispersion relation? When, say, electron density is low and you are at the bottom of the conduction band. So it worked like in a continuum. I say, do you worry about the bandwidth at this point? And usually people say, okay, why? And this will be precisely my argument. So the moment you start doing it, and you assume that you are talking about the bottom of the conduction band, and this makes the calculation easy, you finish the calculation, and I will simply claim that all of this is completely wrong. And I'll explain why. It's also related to my statement that you cannot live without the Feynman diagrams. But if you do Feynman diagrams, just watch out continuously. And this is precisely the lesson which we learned from Migdal-Ashberg theory, the way how it will develop. Looks like you are in a perfect spot. You have very small parameter. You can enjoy the perturbation theory is nice. And you have no idea what's lurking at a very high diagrammatic extension order, and you never know it unless you actually think outside of Feynman diagrams, which means they're useful, but knowing everything else is probably as useful because it can completely nullify all your efforts diagrammatically. Okay, so let's see how the story goes. So what is Migdal-Ashberg theory? Again, I will just do something which is more or less typical for any discussion. What kind of dispersion relation you will choose here? You can choose the parabolic dispersion relation or tight binding dispersion relation for the sake of the discussion, sure. But I need the bandwidth ultimately, because I'm talking about a real material. So yes, it's not infinite bandwidth. So we start with this Hamiltonian. So this is some dispersion relation for the electrons. I will assume that, well, we have, without the interactions, we have well-defined Fermi surface, and the Fermi energy is much bigger than the typical phonon frequency. Again, pretty much typical situation when the Migdal-Ashberg setup is discussed. So, okay, free fermions with Fermi energy much bigger than phonon frequency, typical phonon frequency. Well, then for simplicity, again, I will consider one branch of phonon excitations. So this is the phonon dispersion relation. Again, I'm counting energy from the ground state of the harmonic oscillator. It's not a big deal. It's totally general. And then I have some coupling. I will write it down in this particular form. That's again more or less canonical for many books to include square root of double omega 0 q in denominator, and then g is the coupling constant. Whether you want to attach the square root to the g and write down g bar, it's up to the convention. So I will just use whatever is written more or less in my favorite AG, Abrikosov, Gatkov, Zelashensky books. So that's how it's defined. And then this is simply describing the process. Electron density couples to the displacement of the atom. So electron is scattered because this is the Fourier component of the electron density. The electron is scattered from k to k plus q. At the same time, you emit a phonon with momentum. You remove this one, create this one. At the same time, extra momentum is carried by the boson, so it has to be probably q dagger. But sorry for the notations. But that's the Hamiltonian. I also have the definition of what I will call Baer coupling. I will do it with the notation Migdal-Ashberg because you'll see a little bit later. There's another community. They're not doing Fermi liquid. They're doing polarons. They just go to an opposite limit. They want to study, say, strong coupling when you don't have a Fermi surface, you just have single particles. Assuming that Fermi energy much smaller than omega 0, the totally different limit. And they use a different definition for the coupling constant. That's why I'm saying, okay, my definition is canonical as in the Migdal-Ashberg theory. So which means the coupling constant is defined as taking this construction. It can be a function of incoming electron momentum, which is k, function of k prime or momentum transfer in general. That's why I mentioned it here. Well, divided by omega 0. That's the phonon dispersion relation, k minus k prime squared. And this is averaged over the Fermi surface, which means k is on the Fermi surface, k prime is on the Fermi surface. And you have to average this construction on the Fermi surface, multiply by the density of states. It's a dimensionless number. Well, from power counting, you see the g is energy 3/2, power 3/2. So if it's energy, then it's energy cube divided by energy squared. So it's energy, density of state, dimensionless number. So that's the canonical definition of Baer coupling. Why Baer? Well, because it's defined through the phonon spectrum in my Hamiltonian. Okay, so that's the setup. And then people say, okay, yeah, what are the properties of electrons given this Hamiltonian? And this is what's formally, you don't even have to attach the name Ashberg to this because I will not be discussing superconductivity at all. So It's the basic ingredient to discuss superconductivity due to electron phonons, and the first basic step starts from understanding properties of the normal state. I will not discuss superconductivity in my talk now, but I simply want to understand, okay, well, what are properties of the normal state, say the Green's functions, how the system behaves, before I go superconducting. Okay, so you start calculating Feynman diagrams to understand, well, how, for example, the electron propagator will change. That's how I start. So if I have three bosons, that's the propagator for three bosons. Yeah, of course, you can see if I go to real frequency axis, I will do it every finite. I will use notations for finite temperature. So this is Matsubara, but if you want to do real frequency, just do the weak rotation, omega to I omega. So it has poles for omega 0, for omega equals omega 0. So that's the typical structure of the bosonic propagator. I attach the coupling constant here just for convenience, not to mention it too frequently. Sometimes, well, you'd say 1 and coupling constant goes separately. So this is my D. Well, this is ideal Green's function. But if I have interactions, the Green's function will be modified and I will generate self-energy. And then you say, okay, well, let's start doing perturbation theory in lambda, assuming that my coupling constant is small enough. So you start doing it. In the lowest order perturbation theory, I have only two diagrams. One completely ignored and thrown away almost in any book, just not paying attention. For a very simple reason. Well, because this is the same as simply shifting the chemical potential. So if you say I want to do my calculation in the canonical ensemble or near canonical ensemble, yeah, probably there is some chemical potential shift, but simply make it the original physical chemical potential bigger, then this will subtract, and that's the one which I'm using in the calculation. That's pretty standard, that the chemical potential shift, nobody is even paying attention. Dangerous. Keep track. Yeah, I agree that for almost all arguments, this is totally irrelevant, except one. When you start computing the energy of the ground state, and somebody else says, I have a competitor. Then you say, oh, wait a second. Yeah, let's go back. If I have a particular density of electrons, the density is fixed. This is an important contribution to energy. Diagrammatically, if you want to discuss the state is stable, this is just renormalizing the chemical potential, not a big deal. The moment somebody says, I have a different state in energy, you immediately go back and start paying attention to what the Hartree term is telling you. Yeah, it's very simple term, so that's the answer for the Hartree term. Now, why it's so simple? It simply tells you that this is Bayer coupling constant here and the Bayer dispersion relation for phonons. You say, okay, why? Well, you say, okay, well, maybe I'll try to renormalize D by electron phonon bubble. But the moment you try to introduce a bubble in the middle, it will look like I have a bubble, then another line and another bubble. I say, wait, sorry, this is renormalization of the Green's function. The phonon propagator is still the first one, which is attached to the horizontal line. The first one is still the Bayer spectrum. Whatever happens after the first bubble, it's none of your business. This is renormalization of the Green's function. So that's why in this diagram, D is based on the Bayer phonon dispersion, omega 0. So the parameter from the original Hamiltonian. Well, then you also have another diagram, which is called, this is Hartree, this is called Fock. It's a formal kind of name, doesn't matter much. So I have to compute those two pieces. And the second piece, probably I will not compute and not to go into details. You can read it in any book how it's done. It more or less says that, well, okay, the most important part of this diagram, it can be even defined self-consistently, which means I don't even have to use G0 in this case. I can use even G with this because this sigma happens to have very simple properties. It looks as if it just simply changes the coefficient in front of the imaginary part. So if I just add this one and look at this one, it simply says the coefficient in front of I omega is renormalized and it's getting 1 plus additional piece, which is given by lambda. And that's why if you try to do it self-consistently, essentially nothing changes. Okay, so that's how it works. Of course, having an extractor coefficient here, if I pull it out, it will renormalize the spectrum by 1 divided 1 over 1 plus lambda as well. So which means your effective mass will get a little bit heavier by the same amount, 1 plus lambda.
Well, sorry, what makes it to be independent of momentum? What makes it to be independent of momentum?
It depends on momentum, but very, very weakly. So essentially, it will simply just go to the bandwidth at the boundary, but the contribution coming from too close to the Fermi surface from principal path integral is just nothing. Well, we simply have to write down expressions, and once you start taking an integral close to the Fermi surface, you see there is no contribution.
Yeah. The correction to the Monon-Green's function?
Yeah, we'll come to this. Yeah, so I just started. Again, I'm not calculating diagrams except just simply making one example for the school. Just saying, okay, once you have a graph, it's very easy to write a graph. Wonderful. Then what happens first? You zoom in to the graph and put in indices. Once you put in indices, you start writing down expressions for all the functions. That's what I did here. So that's the answer for the bosonic propagator, which I already mentioned. That's the mathematical expression for this line. Then you go to the bubble. You say, okay, the bubble has momentum k. Why it's 0, 0? Because if you, by momentum conservation, if this was momentum k, the same momentum came back. So the momentum going along the line by momentum conservation has to be 0. Same about the frequency. That's why it's 0 frequency, 0 momentum. Now for this one, I have to go through the summation of all possible frequencies, all possible momenta, and the spin index. So that's my bubble. Well, okay, so you do the exercise. So for spin, it's 2, assuming that the Green's function is spin independent. It's the same expression. You say, okay, do we know the Green's function? I say, I don't care. Why I don't care? Because if I sum through all the frequencies here, well, it's the same as doing Green's function at 0 time. It's Fourier transform. So if you sum up through all the frequencies without any argument, you're just doing tau equals 0 in Fourier. Okay, tau equals 0, but for tau equals 0, we're facing the average. Yeah, it's highly non-perturbative, whatever is many-body state. You don't even care. It's not about Migdal-Ashberg theory. Just in any theory of interacting fermions, the moment you just face this object, this is just the occupation number. It's not Fermi function. I'm not saying this is Fermi function. This is just occupation number in momentum state k. While assuming I don't break any symmetry between spin up and spin down, so I already have spin up, spin factor of 2 here. So we're done because I have to sum through all momentum states, occupation numbers in momentum state k. So I'm talking about total density of electrons. And that's how I finish the calculation of the Hartree diagram. Again, I do the easiest job, of course, because the moment I write down the fork, I have to take integrals and it's much more laborious. But that's how it works. Literally, you transform the drawing into mathematical expression, you finish the mathematical expression, and that's how the technique works. And making drawings are extremely easy. And that's what we saw from Andrei, for example, yesterday. You say, oh, I have fork diagrams. 1, 2, 3, 4 written. More or less your job is finished. Because once you have drawings, just do the proper signs, because that's exactly what we face here. You say, okay, well, this is density, this is g squared over omega 0. Why do I have minus? Okay, this is from diagrammatic rules. They say if you see in the diagram a loop, please add minus sign. Yes.
About what you already said, but just for everyone to know better. Normally, people would say we don't care about this Hartree diagram because we don't know what bare mu is. You put some mu, we don't know what it is.
Yeah.
Finally have this relation that total density is n expressed in terms of Green function. This is normally equation for the dressed mu.
Totally agree.
So why don't we say that mu plus this term will...
Absolutely, you can say it. I totally agree with you. For the grand canonical discussion, that's exactly what you do. It's totally irrelevant. But the moment I want to compare energies of two states at a given density, I don't even care about your mu, how you define it, what's bare, what's not bare. I am having a discussion in a canonical ensemble. Any discussion in canonical ensemble says, please tell me what is the energy coming from this term. I have to count all terms in energy. And this is an important contribution. It's not about chemical potential anymore. It's about energy in the canonical ensemble. What is the energy of the system at a given density? This is energy contribution. Well, you probably know it. Well, okay, you say, don't do sigma, just do the all closed diagrams and compute the energy of the system. You'll immediately have loop D, another loop. This will be n squared, but I say, okay, chemical potential, okay, energy per particle. You just slash it by m, and that's the contribution. So if I take this one multiplied by the number of particles, this is my total energy of n particle. So for energy discussion, I need it. In terms of chemical potential, I totally agree with you. Just throw it away. And that's why it's nobody in the book will even care about this term. They say, why even mention?
Is that exactly what you said?
Yeah, yeah.
It's with two bubbles and interaction.
Yeah. For energy, it's important. For the discussion in the grand canonical ensemble, totally unimportant. Just renormalize your chemical potential and you do the same without paying attention to factor term. Now then, on top of everything, there is what's called Migdal-Eliasberg. And unfortunately, I have to say the word theorem because that's how it's presented in the literature. And the whole talk is more or less that there is no theorem ever in diagrammatic technique. What is the theorem? The theorem is the statement about the lowest order correction, but then the theory is generalized. The statement is generalized. Okay, forget about vertex corrections to arbitrary order. And they say, okay, that's where you're just making a mistake by generalizing the statement theory. So formally, Migdal-Eliasberg theorem says that the leading vertex correction is small relative to the term which we already computed. Why it is small? So if I say, okay, well, the Bayer coupling, say coupling G, which I have here. So, okay, the Bayer coupling is given, but now I say, okay, well, of course, electron can go from one state to another state by emitting a phonon. But at the same time, maybe before this happens, I emit another phonon, then emit this one, and then absorb it back. And this works like the same process. So the electron is scattered, only one phonon is emitted, but there is a virtual state which is dressing the process. You say, should I worry about this? Will this renormalize my coupling, which I have here substantially? You say, okay, yeah, let's do the estimate. So I do have an integral here over the Green's function, and the propagator D. And then you simply do the power counting, assuming that your momentum transfer is not small. Because for any discussion of superconductivity, remember, I have to average the coupling over the Fermi surface. So which means I have to assume that Q is not a small number. If Q goes to 0, it's slightly different discussion, but if Q is generically comparable to K-Fermi, that's what I will consider. You do power counting. What is typical behavior of a Green's function? It's 1 over Fermi energy if my integrals are not restricted in momentum space. And they are not. So Green's function 1 over E squared. Phonon propagator contains omega squared in denominator. This will limit your integrals over the frequency because the phonon propagator decays as 1 over frequency squared. Even if I don't attach anything to the electronic propagators because they go to large momenta, still the frequency will be killed by the D. So which means, yes, I have this one will simply limit the measure of integration over frequency to omega D. And then my power counting is over. I have the bosonic propagator, that's the typical value, typical frequency, and after integration G, you do the estimate, everything goes here, and you discover that, well, the whole diagram is proportional to lambda, and a small parameter, dB frequency divided by Fermi energy. And that's what goes into the name of Migdal theorem. Because why it's beautiful? Because you do the lowest order graph, and your job is over. You don't have to worry about high order graphs because this vertex correction is small. Another one is dressing the previous one is small. Rainbow, okay, this is small. This is also small. You go into powers of lambda times omega D divided by Fermi energy. So you say, okay, yeah, if I don't want to be accurate at this level, forget about those diagrams. So the lowest order diagrams completely solve my problem about what electrons are doing in the normal Fermi liquid state. So that's the essence of, call it Migdal theorem. And then simply Migdal-Eliasberg is just using it in my gap function equation to get TC and ultimately even the gap equation below TC. So the generalization. So this is the essence of Migdal-Eliasberg theorem. Do the lowest order diagrams. They're weakly renormalizing or maybe slightly strongly renormalizing the Green's function by the Z factor, but otherwise this is it. So that's what you will read in every book about Migdal-Eliasberg. Now my question will be, okay, well, this looks like all of this is valid, not only for lambda much smaller than 1, but also for lambda bigger than 1. Because if this ratio is very small, typically we call it adiabatic ratio, simply telling that, well, typical energies of electrons are much, much bigger than typical energies for the lattice. Adiabatic in the sense that you say, okay, electrons are flying so fast, then the lattice is barely reacting to a particular electron. So which means there is adiabaticity that electrons will more or less try to adjust whatever the lattice is doing. So again, much lower dynamics in the lattice than in the Fermi liquid. Okay. So looks like everything is okay as long as I don't care about this parameter. I can go to lambda bigger than 1. And then you can read books and papers that you can actually go to lambda much bigger than 1. And for example, TC will grow as square root of lambda, and I will try to deny this claim. But you need details between. Without details, okay, it sounds sufficient. Now, you say, okay, well, this is perfect setup. Why do I worry? Why do I worry that for lambda of 41, maybe even lambda less than 1, all of this can break? I already mentioned there is other community of people that are considering single particles. And they discuss polarons, they discuss bipolarons. It has nothing to do with Fermi surface or Fermi liquid. And you say, okay, yeah, but this physics actually outside of Fermi liquid, but what if this discussion of people do for polarons and bipolarons has something to do with McDowell-Ashberg theory in terms of competing in terms of energies? They are totally disjoint discussions. I cannot project one on another easily, just there is no way. But they are talking about the same Hamiltonian, simply at different densities. So formally you say, okay, I would like to connect the two fields. I at least would like to see how, for example, from the same Hamiltonian, depending on density, how one can emerge from the other. And what does it mean for the coupling constant? That's kind of one thing. Because often in this physics, you find that particles are extremely heavy. And then this becomes interesting. Well, and there is second piece, which I already told you. If you do Feynman diagrams, always watch out. Why? We have a small cup parameter. Doesn't matter how small. But then you say, okay, of course, if I do diagrams of 41, 2, 3, 4, 5, I'm perfect. I get smaller and smaller and smaller corrections. But then please pay attention that if you do Feynman diagrams, and if you simply start counting how many diagrams do I have at order n, nothing can save you from n factorial. You do self-consistencies, renormalizations, summations. I know, Hayden's formulation in terms of renormalized 3-point vertices. Nothing will help you. The number of graphs at high order always scales as n factorial. Maybe double n factorial, double n, double factorial, but it's roughly the same scaling up to a power. So what do we do? No matter how small is my parameter, I may be happy with my perturbation theory for n equal 1, 2, 3, because, okay, so probably it's not even lambda, but g, if I call this g, this is g to power n. But even if lambda is here and lambda is much smaller than 1, you say, okay, this is still a divergent series. What do I do about it? What does it mean? This is literally denying the theorem as is. It just says, okay, potentially you have to explore what will happen if you go to very high order. And when you explore what happens to go to very high order, maybe you will find out that, yes, you are doing fine. And then your perturbation theory is justified. But unless you investigate this behavior, probably you're not safe. What if what you are doing has nothing to do with what will happen at very high expansion order, and that's what will kill your perturbation theory completely? You always have to worry, and strictly speaking, yes, we all have to live like this because this is generic. I'm slightly cheating here, so I will say a little bit more about this later.
Small question, is the things in the box,
could you please speak louder?
Is the statement in the box specific to the bipolar physics, or it's
Or it's not specific to anything?
in general?
Any interacting Fermi system or bosonic system will always have the same property. The number of graphs will explode exponentially. I will say a little bit more about this. Right now, this is kind of an idea. Take this not as a mathematically rigorous statement. Take it as a motivation to discuss. The number of graphs will be n factorial. Coupling constant will stay here. But what's missing here is just some other coefficient an, which depends on, take all the integrals. Yes, coupling constant factors out. Number of graphs is known. But suddenly I say, okay, all graphs contribute with the same sign and the contribution is n factorial. The answer is no. So strictly speaking, I have to say, okay, that's the sum over n, but instead of n factorial, you have to put here sum over all graphs. The number of graphs is factorial, but what the sum of all graphs will give you at n is not known. The number of graphs is at factorial. I'm just saying putting here n factorial to put the number of graphs, assuming that all of them will contribute roughly the same. Not a big deal. And that's where I'm slightly cheating. With bosons, that's precisely what will happen. You will always face this. But with fermions, there is an alternative, and I will discuss it. So this is just to motivate that you are not safe no matter how small is the coupling constant.
What some RPA like formation work?
RPA is simply doing something probably related to my previous talk as well. You suppose you face divergent series and you decided to sum only some of the terms. You can produce any answer you like. So this is known for divergent series. You can, unless this is kind of divergent in the sense that everything is plus, plus, plus. Suppose you have series which diverge but alternating in sign. If I pick up the proper terms, I can produce any answer I like.
Just saying that you gave the answer already, is that n factorial is the total number of graphs.
Yeah, it's
If
the
sum of
total. Yeah,
particular
that's why I'm
series,
saying this is rather an image for the sum through all graphs at order n. It's not necessarily factorial. For bosons, it is factorial. For fermions, I will give you an alternative. Yeah.
Superconductivity is just one particular letter series when instead of n factorial, you get one.
Yeah. Well, this is second motivation. I have to do something better. And finally, I didn't discuss it yet on my graphs, and that's what I will discuss probably almost first. Strictly speaking, yes, when I start doing diagrams, I only paid attention to what happens to electrons, but I didn't discuss what will happen to phonons because of the same coupling. And we go to the renormalization of the phonon spectrum. Because if I renormalize phonon spectrum and suddenly one of the phonon frequency will touch zero, it literally means that this is extremely soft mode, and the crystal actually wants to go to a different crystalline structure. Within the theory, probably you say, okay, you touch zero, and this is a continuous process as lambda getting smaller and smaller, but usually structural phase transitions are first order, which means you will not be able to soften the phonon mode all the way to zero. Before actually the touching zero happens, there is some structural transition of first order. You reconstruct the unit cell and the spectrum is again finite. So let me discuss this last point. The first 2 points are more technically involved. So that's what was missing in my previous discussion. You say, okay, yeah, we have to take care of electron phonon coupling and renormalizing the phonon spectrum. And again, Migdal's theorem makes everything very easy because I don't have vertex direction. So the only thing which is left is the phonon is propagating. Well, what may happen that this phonon is absorbed at the expense of scattering an electron, creating an electron hole pair. That's what I mean. Just particle hole pair, which Andrei already discussed, and then the phonon is emitted later. And it can happen many, many, many times. I don't have to do vertex corrections. I don't have to do additional lines. All of this is small by the parameter which I already mentioned, which is adiabatic parameter. So this is the dominant contribution to the renormalization of phonon spectrum, and it's very easy. All I have to do is just to compute the polarization bubble. Well, you do the computation of the polarization bubble and put it in denominator because I face standard geometric series, Dyson equation. You immediately see that if it's a dashed line, and this is P, but if I just put here the square bracket, it will start with dashed line. Dashed line P is cut off, so dashed line P, and I repeat the same. So the equation looks like d bar equals d minus d polarization bubble d bar. So in terms of inverse, that's the solution for the geometric series. Well, now just plug in the expressions. So d0, sorry, this is 0. So d0 is given by this expression. We already had it. Omega m squared, omega 0 squared, that's the inverse of d0. We already had this expression. Well, I had g squared, so we'll pull it out. So I have g squared times the polarization bubble. So this is nothing but renormalization of the phonon spectrum. But then you say, okay, yeah, but here I'm talking about the electrons. this frequency is the bosonic frequency of phonons. And again, everything related to phonons is much, much smaller than Fermi energy. And typical momentum transfer is not small. So I'm talking about the polarization bubble when V Fermi Q is much, much bigger than frequency. So which means with the same accuracy as I dropped the corrections to the vertex, I can assume that P can be replaced by the static limit. Yeah, the polarization bubble is just summation of two Green's functions through the momentum and frequencies, but I can put here frequency equals 0. Which means the frequency which coming to the bubble can be put to 0 because momentum transfer is typically large. So that's kind of, again, standard consideration. And again, everything simplifies. So I immediately see that, okay, I don't have to worry frequency here. So this immediately gives me the new spectrum. Because if P is only a function of Q, we're done. Again, I'm repeating standard considerations, which you will see everywhere, but that's how they work. So we have the phonon spectrum, because I will have omega m squared, omega 0 squared, and this is the function of Q only, because I can put 0 there with the same good accuracy. So that's the renormalization of the phonon spectrum. Yeah, it's given by G squared. Okay. Well, now that's if I have this definition of renormalized phonon spectrum, that's what I have here. So this is my renormalized propagator, because it's 1 over G squared, omega m squared plus renormalized spectrum. So it looks the same as it was before. Nothing has changed, except the bare phonon frequency now is replaced with renormalized phonon spectrum. Any question? And now kind of the final piece. You say, oh, but if I renormalize the phonon spectrum, because I still try to work starting from the Hamiltonian. If I renormalize the phonon spectrum, please go back and recalculate properties of your electrons. Because remember that instead of D, when I compute self-energy for the electrons, the Fock one, in the Hartree term, I already proved to you that in the Hartree term, it's D0. It's an unrenormalized spectrum, because any other diagram that you try to put there will simply renormalize G, but this goes to the total density. But for the Fock diagram, I have to use D bar, because you start computing the Fock diagram, you have a phonon, but this phonon can create a bubble, another bubble, another bubble. So the propagator in the Fock diagram has to be this one, renormalized. Well, which means, yeah, I have to reconsider and introduce a different, yep.
So here you choose that your omega m is much less than the BFQ. There's a choice you make. Like you are only.
Yeah, the bi-frequency is much more than Fermi energy through the entire discussion of Migdal-Agterberg. I never ever assume to violate it. So Fermi energy is always much smaller than the bi-frequency.
But
Fermi energy is much smaller than the typical phonon frequency. Yeah. Well, but if you make your spectrum softer, because if you look at this expression for P, say at the RPA level, it's a negative function, so it definitely will lead to the softening. I did say something wrong. No, the other one, yes, sorry. Migdal-Agterberg is Fermi energy much bigger than omega 0. Remember this, even if I say otherwise. Okay, so that's the end of this discussion. It says, okay, yeah, there is a danger that if I keep increasing the coupling constant, I may actually face the problem that the phonon spectrum will try to touch 0. Maybe not completely because of the first order structural transition, but it can get sufficiently soft. Not only the entire spectrum is getting slightly softer, also the particular momentum Q, maybe it can go almost all the way to 0. So that's the statement, which probably can limit your ability to go to very large coupling constant, the bare one. Why the bare one? Well, look what I have here for the renormalized phonon spectrum. That's the bare phonon dispersion relation. That's the coupling constant not involving any dispersion relation. And this is properties of the electrons. So the way how it touches 0 is entirely the business of the bare coupling constant in your Hamiltonian. And more or less by easy arguments, we'll see it. Okay, if you say, okay, well, suppose I divide everything by omega 0, just assume. So say, okay, well, I have something here. The polarization operator, for example, for 0Q, it's density of state, just to make an estimate. So I have density of states, G squared, compared to omega 0. That's roughly lambda equals 1. If you do it for the parabolic dispersion relation, actually you figure out that, okay, for lambda 0 Migdal-Ashberg, at 1/2, you will try to create an instability. So if I assume, for example, that phonon dispersion relation is a constant, and parabolic dispersion relation for the electron, that's what most books are doing, you will find out that lambda 0 equals 1/2. That's precisely when the phonon spectrum will be solved. Okay. But you already see it from dimensionless kind of estimates, creating a dimensionless number. If I put omega 0 here in denominator, that's roughly unity. More precise calculation says 1/2 for a particular choice of dispersion relation. That's one problem which potentially can limit lambda 0 Migdal-Ashberg. This is well known. Again, nobody is discussing this instability or questioning it. It's definitely there. But this leads immediately to reconsideration of what do I call effective coupling constant for the Migdal-Ashberg in terms of superconductivity and the rest. Because remember when I was doing the Fock diagram, the way how electrons will interact in the Cooper ladder, everything now will be based on d bar, the renormalized phonon spectrum. Because the moment you emit a phonon, the spectrum is renormalized and we already have the expression for the renormalized phonon propagator. You have to replace omega 0 with omega renormalized. The true, some people will call it the true phonon spectrum. So I have to define lambda Migdal-Ashberg now without 0, because it's kind of highly nonlinear relation at this point. Yes, I have the Bayer coupling constant G, it's still there. But when I define this parameter, it has renormalized phonon spectrum in denominator. And that's the one which will enter for the next level of doing the theory. Everywhere I have to write down d bar when I discuss properties of electrons. So that's where it will show up, except for energy. Everywhere else, it will show up in this combination. So you define lambda Migdal-Ashberg. Now it has phonon frequency, which is softened in denominator. And potentially you say, okay, I cannot cross lambda 0 bigger than 0.5, for example. But at the same time, as lambda 0 is approaching 0.5, it may happen that because of the phonon softening, lambda Migdal-Ashberg can be bigger than 1. And that's precisely the discussion many people have. Okay, how you can have Migdal-Ashberg theory with large coupling constant. That's the one which will give you superconductivity and the rest. Okay, and that's why kind of in the literature, you see precisely this quantity, which is mentioned as Migdal-Ashberg coupling, not the original 0, but the renormalized one. And in principle, this one can be bigger than 1 or much bigger than 1. But then you say, okay, I don't care because I have Migdal's theorem, which says vertex corrections are still irrelevant, even though this one can be much bigger than 1. Okay. I probably already said all of that. Okay. Any question at this point? Again, so far I was 1 year old when all of this was done. Okay. No questions? So now we natural question, you say, okay, well, but how big lambda Migdal-Ashberg can be? That's where I will start deviating from a lot of statements which are even published recently. I will say, okay, I have to investigate this issue because in principle, if you ask academic question, you say, can it go as large as you want easily? I say, in principle, yes. Just imagine that the following is true. I will do artificial fine-tuning of my model. What is artificial fine-tuning? I say, imagine that my omega 0 of u is such a function that it's a very small number. Well, this is positive. Remember that p is negative. That my original phonon spectrum is a very small number and knows everything about the, even without coupling. Because remember, this is omega 0. That's why I'm calling it artificial fine-tuning. By artificial fine-tuning, the bare phonon frequency, before you couple to electrons, suddenly knows everything about those electrons. So it's some number times the polarization function of my electrons at particular density. So by some miracle, phonons all by themselves without electrons already know what the electrons will do. Okay? Suppose this is true. Well, then if I try to renormalize, I will face this expression. We have seen it before, bare spectrum plus g squared times pq. And you immediately see that when g squared equals c, I will create a phonon spectrum which is absolutely flat, delta squared everywhere, momentum independent. And that's precisely what you can read also in some papers. People say, yeah, forget about original phonon dispersion relation. I don't care. Let's consider the model when the final renormalized phonon spectrum is an Einstein phonon, dispersion momentum independent. That's what goes into this statement. Bare phonon spectrum has to know everything about electrons before you even switch the coupling. Then you switch on the coupling, and that's the only way how you can get momentum independent dispersion relation for the physical phonon. That's why I call it absolutely artificial. But if you do it, well, you see a phonon spectrum in denominator. Typically, you say, okay, my lambda will grow as 1 over delta squared. And delta can be made as small as I want in my academic consideration. So I will just blow my lambda as 1 over delta squared. Okay. Just simply remember this. Yes, artificial, but in principle, you say, okay, this can happen. Well, at the same time, please don't forget that, okay, when you compute everything about electron phonon coupling, you also need typical frequency of phonons. So this is also about the physical spectrum. This will also scale to 0 now as delta. But remember, in superconductivity, you have a prefactor. Debye frequency, typical phonon frequency, and then everything else. But the frequency of those phonons, now it's also soft. Will come into the prefactor of the TC. Just don't forget this. And for me, it's important, but I'm trying to work from the original Hamiltonian. I always refer to this as artificial because I written the Hamiltonian. If I didn't have original Hamiltonian, everything looks pretty innocent, that the actual phonon spectrum is momentum independent, doesn't depend even on coupling. No, all of this is written in such a way that because of the coupling, I maybe came to this particular expression. But if I created this expression, the Debye frequency is also proportional to delta. Okay, so what is more realistic? More realistic is that, well, okay, the bare phonon dispersion is something, electron polarization is something else. You switch on the coupling, and first you will touch 0 at some momentum point. Of course, I know, as Daniel explained, of course, because of crystal symmetry, it's a star of different momentum points related by point group. So it's just not one point, but maybe a small set of points related by symmetry. This just multiplies by the number of those points, but otherwise it's the same. So I have some particular value of Q when the phonon spectrum will try to touch 0. Well, okay, so you start writing it or say, okay, this is what I get if I get to this point. This is how small my frequency will be if I try to get to this point. So when Q goes to Q0, I will create some small number. Suppose this number is small because then the first order phase transition will happen. Or you can soften and even further, and delta, academically, delta can even go to 0 without first phase transition. So imagine the delta can go to 0. But there is a momentum dependence. I go to 0, but for example, I can put it exactly 0. But then omega squared is the parabola, more or less because of analytic behavior of original phonon spectrum and the polarization operator, roughly, not always, but kind of generically. Well, but then the phonon spectrum is simply, I don't know, like sound wave out of this particular point. Also related to once you form a phase transition, structural phase transition, this momentum somehow will be related to new Brillouin zone, and this will be the new sound wave mode, say having more atoms in the unit cell. Okay, that's the more realistic scenario, how the softening will happen. It's momentum dependent. Well, but I have to do the averaging of the Fermi surface. Well, so I'll just simply plug in this expression, the square of the spectrum into this averaging. I average over the Fermi surface, so it's kind of two-dimensional integral over Q because it's kind of limited. Well, but then you immediately see that, for example, in 3 dimensions, I have 2 integrals and I have 1 over Q squared. Even if delta is 0, the divergence is only logarithmic. So it's not as academic as I had before. 1 over delta squared, that's how the coupling constant will blow. No, it will increase, definitely. but it will be limited by logarithmic behavior, which means unless delta is outrageously small, your lambda will not grow too far. But again, first order phase transition probably will stop you. So that's one. So I cannot go too far in 3D. I can do much better in 2D because I have one integral and I have q squared, so divergence is first power. So probably my lambda can grow as 1 over delta. Which means it is possible to have lambda much bigger than 1. Yep.
What is the physical origin where you can like forcibly gap out the 0 point by putting delta by hand? Or is it by hand or is it there's some mechanism?
Well, because you have different contributions to the phonon spectrum, and electron polarization may want the lattice to reconstruct.
But that's May, right? But that's May once, right? Not guaranteed.
It's not guaranteed. It depends on the coupling constant. No, when I just write it down, the way how this is softened depends on the coupling. I have original spectrum which was not soft anywhere. But then polarization operator and original phonon spectrum, they almost compensate each other, and I try to touch 0 at a particular momentum point. And I'm writing down the most trivial Taylor series expansion, what I can do for omega squared when I try to touch a constant. That's probably I didn't touch yet, so it's a number, plus some Taylor series expansion around this point. Why I'm writing down this way? Because, okay, well, probably this is even more dangerous because I'm trying to make it parabolic. If it's linear, like cusp, this will be even less dangerous. I'm trying to create the most dangerous situation I can imagine. Because my point is kind of to discuss academically whether you can do something, I know, good for large coupling constant. Yeah, so I make it parabolic, but otherwise you say, okay, if it's a linear cusp, you'll remove another integral. Even in 2D, this will be low. But this is kind of non-analyticity in the middle of the brilliant zone, not sure. Okay. What do I learn from this discussion is one. If I want large, without academic previous slide, when I just do something very artificial, if I want large electron phonon coupling constant, it's almost necessarily by this discussion, I have to link it to the highly dispersive phonon branch. Because that's when I really see that you can go to lambda renormalized much bigger than 0.5. Because if lambda is not renormalized by the phonon spectrum, I cannot cross, in terms of lambda 0, I cannot cross 1/2. This will limit me. The phonon spectrum, if I go to original coupling constant, it will try to soften one spectrum and it will try to touch the 0 for lambda 0 equals 1/2. At this point, probably renormalized lambda will try to increase. And if you do find that lambda is much bigger than 1/2, say 1 or 2, almost necessarily this is because of the phonon spectrum softening, which means the phonon spectrum has to be highly dispersive.
Right.
Yep.
We are 1/2. We know what we're talking about. In your
Oh, in my discussion, there is no 1/2
appears.
Hmm?
Where 1/2 appears. I guess
It was appearing before. It was appearing here. Sorry. That's where 1/2 appeared. This combination, g squared pi, which is density of state, that's small q, for example, but roughly it's the scale of the pi. G squared, density of states divided by omega 0, that's lambda 0. When lambda 0 is a 41, I expect the phonon spectrum to start collapsing. I was saying 1/2 comes if I specify the dispersion relation and I specify k squared over double m as dispersion relation for electron. Then you have 1/2. Otherwise, some number of order 1. 0.5, actually you'll see numerical calculations, it's 0.25. Maybe under some conditions you can make it 0.75. But I have never seen 0.75. It was always smaller than 0.5. You'll see. But that's the estimate. So lambda 0 cannot be bigger than 1 from this estimate roughly. To have renormalized coupling very large, you have to have a highly dispersive phonon spectrum. That's one lesson. Yep.
At the bare level, what is omega naught q? Is it like that?
Oh, just anything you like.
Like Einstein type phonon, like constant?
It can be Einstein phonon, but then the polarization will soften it at a particular q. Not everywhere, at a particular q.
So you start with a non-dispersive phonon?
Yeah, I'll show you some graphs here, nothing special, yeah.
No, I'm saying you start with
You start non-dispersive, you'll get dispersion, and it will try to touch 0 at some momentum point. It will get highly dispersive, even though the original one is not.
And if you start from dispersive phonon, not till you get it.
You start with dispersive, you get yet another dispersive, which will try to touch zero. And only then you can have large effective coupling constant. I'll show you the calculation, how it goes. Okay. One question sometimes discussed in the literature is, okay, let's consider the following case. How TC grows up if lambda Migdal-Ashberg, this is always renormalized now. If lambda Migdal-Ashberg is much bigger than 1. And you see a formula which was derived by Alan Dines, that TC will be proportional to Migdal-Ashberg omega d, and some people are extremely happy. They say, oh, it means that superconducting transition temperature can grow without limit when lambda is much bigger than 1. It grows as square root of lambda. And ultimately, temperature can even be much bigger than the phonon spectrum. Again, I started from the Hamiltonian, and I'm saying, well, this is all fake. Why? Even if I do completely artificial, the best possible case for increasing lambda, remember that, well, if the entire spectrum is softened to very small value, lambda will grow as 1 over delta squared. But the Debye frequency itself, the characteristic frequency which I have to use in the expression, is delta itself. Nothing is growing. So it's rather consistent, my statement is consistent, that if I do even artificial fine-tuning of the spectrum and do everything possible for large lambda, I will not get TC growing. I will probably have it to saturate. There is nothing I can do about it because I will saturate to a number, because omega d scales as delta and lambda scales as 1 over delta. I will saturate to a constant. But this is totally artificial. I already tried to convince you that lambda will grow not faster than first power in delta only in 2D. In 3D, it will be even log. But the Debye frequency, which grows for this large lambda, is small. It's still delta. You have large lambda just because you are exchanging soft phonons of this particular frequency. So Debye frequency under normal conditions, not the artificial ones, if omega d is still delta, but lambda is, so it's delta squared, but lambda is 1 over delta because I soften at one point in 1D or just log delta, TC is actually going down. So which means for large lambda, under those conditions, I don't expect that TC will grow.
How you know in this situation that prefactor will be, in this particular case, which you're discussing, that prefactor will be renormalized by frequency?
I cannot answer this question. I didn't do the calculation, so I'm just doing estimates.
Okay.
So my estimates simply say, yeah, I will have to saturate, and even under most artificial conditions, I will saturate to a number. Maybe I will slightly increase and saturate. Maybe I'll go through a maximum and then saturate. And that probably Andrei has some answers which are saying that you will go through a maximum and then separate. And the prefactor will stay roughly Debye frequency divided by some number, like 10 or 2 pi. Sorry, TC maximum will saturate to something which is Debye frequency divided by 10, roughly. You're not supposed to read it anywhere, so that's the first time you see it. So first, I totally deny that TC will grow if you try to increase electron phonon coupling. You can increase electron phonon coupling by doing artificial job. Keep increasing lambda by keeping omega Debye fixed. And that's what's done, just literally. You say, okay, let's fix Debye frequency, so it's not scaling, and let's keep increasing lambda Migdal-Ashberg as a separate parameter. Why? Because you're not doing the Hamiltonian. Because often the entire discussion of Migdal-Ashberg says somebody renormalized the phonon spectrum, so forget it. Now the phonon spectrum is fixed and coupling independent. And that's where everything happens. So you start considering effective discussion. It's an effective discussion. When the spectrum is already renormalized, so don't touch it, but keep increasing the electron phonon coupling as a separate parameter for my theory. Then that's the answer. I am trying to convince you that this is totally inconsistent. When you start from any Hamiltonian, you cannot keep increasing lambda without paying attention that the spectrum is renormalized. It will be renormalized. If you want to increase the coupling constant, do something about your spectrum. It's unavoidable. Okay. So this is one denial. Einstein was wrong, but okay. It's in the same style, but what can I do? Hopefully I convinced you that, okay, my argument was physical enough. Now we just go slightly further and it's even more destructive. I go back to my Hartree term. I say, okay, wait a second. Nice theory, nice Migdal theorem. But let's compute energy. So I start computing energy. So what do I have for the Fermi liquid state? Of course, I have kinetic energy. Sure. So that's the one. You can put tight binding dispersion relation to finish the calculation for kinetic energy. Well, I also have potential energy because I couple two phonons, and we already have our Hartree term. Okay. And then I also have some corrections coming from the Fock diagram. But what I have from Fock diagram, which involves virtual exchange by the phonon, this is like second order perturbation theory when I have denominator, which is the bandwidth. So this will end up with correction, which is small compared to the previous terms by the bifrequency divided by Fermi energy. I will simply drop them because I consider this as a very small correction. So whatever I have from the Fock term is subdominant to the first two, kinetic energy plus the Hartree term. Totally irrelevant if you want to renormalize chemical potential and continue, but absolutely relevant if I want to discuss the energy of the state at a particular density. So this is the calculation which goes into energy of the Fermi liquid state, kinetic energy, and the Hartree diagram or mean field, which gives me this answer, which I already discussed. Okay, this is now kind of full answer for any number of particles you want. I was computing the chemical potential, but the chemical potential is dE over dN. And this was G squared omega 0 times N, but this was the derivative. So the energy is N squared divided by. Okay, suppose I'm sitting in the band. If I'm close to the band, say parabolic dispersion relation, just for the sake of estimate. So you have to do, otherwise you have to do the sum. So that's what we have. And this is the mean field term coming from the Hartree. Again, pretty simple, because this is in terms of Hamiltonian parameters, so it's relatively easy to compute for any model you can imagine. Now I'll do something outrageous. I say, yeah, I'm talking about the Fermi liquid state, but let me stop talking about the Fermi liquid state with large Fermi energy. I'll do something else. I will take two electrons, spin up and spin down, put them on one side, and not allow them to move. You say it's a horrible state because you lose a lot of kinetic energy. I say, fine with me. Lose your kinetic energy. But I will gain energy from the interaction Hamiltonian. The solution is essentially trivial because if I decided to localize all electrons, it means that my density is not dynamic, it's just fixed. I have some Fourier transform how I decided to localize electron pairs. Electron up, electron down, say spin singlet on one side, done. You say it's a stupid state. I say it's stupid state, but exactly solvable one. So don't argue, okay, how stupid, because I will be using variational approach. My state is not the best in energy, I don't care. But if it's better than Fermi liquid, we're done. And that's precisely what I want to estimate. I create a stupid state, localized electron pairs, not moving whatsoever. And that's the Hamiltonian which is remaining. There is no kinetic energy for electrons because I forbid them to move. But this is nothing but the shifted harmonic oscillator. This is B dagger B standard, and this is just linear in X. So just shifted harmonic oscillator. You can easily just find the energy of this state. That's the exact expression. Because MQ simply tells you, okay, how much you have to shift a harmonic oscillator at momentum Q. So that's the answer. And I'll simply rearrange it in the real space. Just go from Fourier representation, simply go straight to the real space representation. That's identically the same expression. Why it's convenient for me? Because I will simply create NR, which is always 2 on one side, always 2 on some other side, maybe some distance away. The two, this is my Hamiltonian, this is exact solution, this is still exact, it's simply identity. It literally says, okay, if I want to consider state with localized pairs, just okay, place them the best possible way given what is the VR function. And VR function is just Fourier transform of whatever I get from here. For example, if the phonon spectrum, bare phonon spectrum, is say flat, it's okay, like a model. This is just a delta function. They said, I don't even care how you will place your pairs, the energy is the same. But on every side, you will have two particles. So n2, another n2. So this is just a factor of 4 times whatever we get from the delta function. So just for the sake of the estimate, suppose I have dispersion less omega 0, not to worry about this one much. It doesn't change much. But I can play different games with this one to arrange pairs differently, maybe checkerboard, maybe just any way you like. So that's the energy. So that's the energy of the bipolar rods. G squared over 2 omega 0 squared 4 coming from here. And this is just n divided by 2. Why n divided by 2? Because I'm talking about the density. How many pairs do I have? Okay, because not the number of electrons, but the number of pairs. That's how much a pair will gain, and that's the number of pairs. So that's the total energy. Okay. Now we have to compare. Fermi liquid has some energy coming from the dispersion relation. Of course, you immediately gain because if they move and this is the bandwidth, I start counting from the bottom of the band, say tight binding model, minus 2 dt. Well, then I add something from Fermi distribution. I have written the expression for small density, but of course, otherwise you have to sum up the tight binding dispersion relation, which everybody can do on a computer. And okay, the Hartley terms. And then this kind of roughly the estimate says at very low density, just do the counting. This is density 2 divided by 3. This is density n. So this term dominates. This is subdominant at low density. So at low density, actually, the energy is roughly sitting at the bottom of the band. Of course, if you have higher density, do the full calculation, no problem. And I have to compare this with this one, but you immediately see what the comparison tells you about the critical coupling constant.
What is capital D again? What is capital D again?
Capital D,
Ah.
dimension of space.
Oh, okay. Thanks.
Well, if you do the tight binding model. Okay, so this is our condition. So it says, okay, well, my stupid variational state will win over the Migdal-Eliashberg type Fermi liquid state. If I just start plugging all the parameters, for example, you say, yeah, at the bottom of the band, I need, but just why I'm doing it. Formally here I'm done. So you say, okay, when G squared over omega 0 squared is bigger than double dt, this is roughly half the bandwidth. So if this combination is bigger than half the bandwidth, my stupid state is better. Now I have to convert it to the original Migdal-Eliashberg parameter because it's based on the averaging over the Fermi surface times the density of state. And that's where the difference will start happening. I say, okay, for density of states, let's do estimate at the bottom. Effective mass is 1 over double T. Again, lattice constant is 1, sorry. If you want to put lattice constant, it's A squared here. So this is effective mass in the tight binding dispersion relation. If I do 2D, density of states per spin is m 2 pi. So this is 1 over 4 pi T. You do it in 3D, this is chi Fermi divided by 4 pi squared T. Okay, so this is my density of states. And now I can form the Migdal-Eliashberg parameter lambda 0, which is given by this expression times the density of states. Simply multiply this number. I say, okay, that's the critical value. So multiply 2 dt by this number. Coping parameter will cancel. And you will be left with the number, which it's at the bottom of the band. So the number is roughly 1 over pi 0.32 in 2D. But in 3D, I suddenly discover something which says, okay, every textbook is wrong. Why? Well, because my lambda 0, according to this discussion, at low density, that's when I can use parabolic dispersion relation. That's precisely what every book is doing. Parabolic dispersion relation, good for the bottom of the conduction band. I see here the factor which is n to power 1/3 because that's coming from the Fermi surface density of states. This parameter is 0.47 if I plug in all the numbers times density to power 1/3. If my occupation number, that's occupation number, is much smaller than 1, I discover that my Migdal-Eliashberg theory loses in energy to the stupid bipolar on state at lambda 0 much less than 1. It's not only that Migdal theorem which was protecting me is wrong. It's also that even without thinking about adiabaticity, for lambda much smaller than 1, for spherical Fermi circuit, if I actually think about lattice regularization and the bandwidth and everything, Migdal-Ashberg theory is completely gone. You have to give way to another state. In this case, it's the state which is, say, localized bipolar. But you say, okay, yeah, but your state is probably not the best one. I say, totally agree. Maybe the actual state for these bipolarons will be bipolarons are moving, because ultimately translational invariant system, they have the chance to go to even lower energy because they can delocalize. Or you can form charge density wave to gain some energy from interactions between bipolar. So my state is probably not even the best one, but it's better than Fermi. So that's the lesson we learned, that and again, those two numbers, if you do parabolic dispersion relation, those two numbers are smaller than when the softening of the phonon spectrum will happen. Because it simply says that at low density, Migdal-Ashberg theory will never grow large coupling constant. Because I cannot soften the phonon spectrum at low density. But the system is already gives way to bipolar. If coupling constant is large enough. The original one. This one. If this one is large enough, because this is not density dependent. This depends only on the band structure, couplings, the spectrum, and the rest. But the Migdal-Ashberg lambda, which is defined by by the theory, this one involves density of states. This one is much less than 1. Yep.
The way you have set up the problem with the bipolarons, like each side.
Unfortunately, here is the air blower, and it's just interfering with how loudly you can say.
So the way you have set up the problem with the bipolarons, with each side being doubly occupied and interaction, it seems like it's a fully filled.
Well, you see, the beauty of variational principle is, well, Laughlin got a Nobel Prize. I just will tell you the story because I was present in the room when people discussed fractional quantum fold. Nobody knew the clue. It was a discussion through all the series. It was Landau Kapitsa Institute. People were giving talks, and suddenly one talk was given by Dima Khmelnytsky. Everybody was interested. Everybody was trying to understand what is the fractional quantum pole, where it's coming from, what's the theory, how to explain all of this. And suddenly Dima said, okay, well, Laughlin suggested this variational state. 5 minutes later, everybody just left the room. They say, okay, we're done. So they just look at the state composed of exact Landau orbitals, and they understood, okay, we're done. So this is precisely the beauty of variational state. So variational state, which I presented, allows me to finish the calculation exactly what's the energy. As long as it's lower than Fermi liquid, forget about the rest. Yes, I cannot be responsible what will happen with bipolaron physics. Those bipolarons likely, and lecture 4 will be actually saying, I know how to solve bipolarons exactly for any electron phonon coupling. I'll just give you example. They are not localized on one side. They have finite sizes often. They move, they have effective masses, they can superconduct as the bosonic liquid. All of this is interesting physics all by itself. I am doing none of this. Yeah, there are much better energies for bipolarons. I'm doing the most stupid one because I can solve it exactly right away and compare. Yeah.
What if there are other competing states that aren't bipolar?
Again, none of my business. Name any other state which is better than this one, and you win. That's precisely the business of variational. The moment you say, okay, I don't like your state, I have another state which is even low in energy, I give up. I go to the corner and say, okay, your state is better. Let's discuss its properties. But it has nothing to do with Fermi liquid anymore. Because once you go to bipolarons, there is no Fermi liquid. It's bosonic degrees of freedom now. Okay, that's something we're trying kind of to finish writing, but that's the answer which I think you will never find anywhere. That Migdal-Ashberg theory can fail for lambda, original lambda, much smaller than 1. Nothing to do with phonons or spectrum softening. I probably have to watch my time. Oh yeah, I have to finish with showing you some graphs. So you extend say, okay, well, I will just do several different Hamiltonians with different phonon dispersion relation, trying to increase the coupling constant and simply to see at what original coupling, original lambda 0, Migdal-Ashberg. When do I collapse the Fermi liquid state to bipolarons? by variational calculation, or where the phonon spectrum will try to touch zero. And at the same time, trying to get some sense of how big lambda Migdal-Ashberg renormalized one can be. Okay, I'll just show them both the way, right away. Suppose I have this phonon spectrum, which is soft at low frequencies and more tough at high momenta. Sorry, at low momenta, it's the minimum, and high momentum is go up. Remember, I have to soften it by polarization operator, and because this is already the smallest number, the softening first will happen at q equals 0. So this is the renormalized spectrum. Okay? When it happens. But then I just noticed the following. So if the function of density, if I try to solve this Hamiltonian, I see that, well, okay, for lambda 0, Migdal-Ashberg, the original Hamiltonian parameter, the system collapses to bipolarons before phonon softening happens. Starting from this density, before my bipolaron state wins, I actually soften the phonon spectrum. That's where I can grow large electron phonon coupling because of the phonon softening. So close to half filling, it's not necessarily that I can claim that bipolarons will destroy the Fermi liquid. No. The breakdown of the Migdal-Ashberg has to go through phonon softening, ultimately growing lambda, and then either phase transition or, say, more interesting physics of non-Fermi liquids, which Andrei probably will discuss with you. What happens if I have soft modes and coupling is strong enough? So something happens on approach to this line but this is in terms of bare lambda. But I can also ask, okay, well, when I collapse to bipolarons, how big was effective lambda Migdal-Ashberg at this point? Because the spectrum still softens a little bit. Of course, there is no phonon softening at low density. That's what I was telling you. Lambda is getting much smaller than 1. Phonon softening is minimal, so renormalized lambda is almost the same. But of course, if I approach this boundary, close to this boundary, yes, I first collapse to bipolarons, and then I create a soft spectrum. But it means that, yeah, I collapse to bipolarons, but my phonon spectrum is already substantially renormalized. That's how high the renormalized lambda can go. The bare one was, say, 1/4. I can grow it even to lambda equals 1 or even slightly more. Not dramatic. So it's almost 0 in the phonon spectrum, but the 0 happens at q equals 0, and the rest is, you know the story. You can change the phonon dispersion. I can start with the bare phonon dispersion in the opposite sense. It's the toughest spectrum for q equals 0, but then it's the softest spectrum close to the Brillouin zone boundary. In this case, the softening first will happen close to the Brillouin zone boundary because of the Van Hoff singularity in the polarization operator. It will kill the phonon frequency first somewhere here. Well, this is along the diagonal, so it will happen at the pi corner. Yeah, I'm doing 3-dimensional cubic lattice. But the same story. You see that Migdal-Ashberg theory at low density fails for lambda 0 much smaller than 1. Spectrum is not renormalized. Here, the spectrum will be renormalized and try to touch 0 at this point. So the effective lambda will grow. Well, but here I'm already creating 0. So I'm at the boundary. At this point, the softening of the spectrum is complete. Well, but the normalized lambda barely went to 0.8 because the divergence is logarithmic. As I was trying to convince you, even if delta goes to 0, I'm doing finite size system, sorry. So the largest system size was 512 cubed. So that's why there is some quantization in the momentum space, which will, of course, limit your log. But yeah, again, the increase is not dramatic. And that's more or less confirming the picture which I was trying to tell you. Probably I can stop at this point. Let me see what I have. Oh, yeah, I have 2 slides. They're a little bit technical. Let me simply just go back to what I was trying to tell you. Diagrammatic technique is still diagrammatic technique. To say, okay, what went wrong with the Migdal theorem, which was saying, yeah, you have small parameter, vertex corrections are small, it's undeniable. Even if lambda is bigger than 1, they are small. But then you go to high order, high order, high order. At this point, you start wondering, in the high order Feynman diagram, what happens there? And there are 2 scenarios. Again, this is the image which says, okay, well, formally, if I assume that all diagrams contribute the same, you have double n factorial. That's the number of terms. But terms for Fermi system, they don't come with the same sign. So call it sign blessing. So that's actually what we do, because we do high order diagrammatics for fermions, and you say why in the strong coupling limit, you see some answers for the homogeneous electron gas for S equal 5. So you say, why not everything just blows away? It doesn't blow away because what I call sign blessing in diagrammatic technique. In diagrammatic technique for fermions, different graphs with different topology, different number of loops, they come with a different sign. I can have double n double factorial graphs, but those graphs can cancel each other. And it may happen that my coefficient, which is coming now from taking integrals from all those topologies. This is the number of topologies. Just factor it out. And this is what do I have per topology after I sum up through all the topologies and take all the integrals. And it may happen that this one is actually goes to 0 as 1 over double n factorial, completely kills the factorial, maybe creates a power law, but then I have finite convergence rate. No matter how small is alpha, this may happen at very high order. But ultimately, in very high order, the sign blessing will help you, and the Migdal theorem works, you have convergent series. But it may happen that for other parameters, I know, given the conditions, you simply close the convergence radius. Now you are outside of the convergence radius, and no matter that perturbation theory is perfect for low orders, ultimately you lose it. So ultimately, you'll see that you're outside of convergence radius, and probably this is a signal that the state has to change. Because contributions coming from low order diagrams are not representative of what the system ultimately wants. Why I'm saying it? Because on the parameters which I mentioned, larger diabetic, smaller diabetic ratio, the bifrequency to Fermi energy, once I create bipolarons and I start solving for their properties, I will find that they are exponentially heavy. How do you get exponentially heavy effective mass starting from the low effective mass? Only by going to diagrams of very high order, and that's what's very well known in the polaron community. So somehow the system at the line when I say bipolarons replace Fermi liquid. If you try to do it in a perturbation theory in the coupling, you will discover that polaron physics is sitting at very high expansion order. Fermi liquid is sitting at low expansion order. And they actually change the balance which state wins. We have one exercise, I will show you the slides, that actually you can kind of slightly play this game, how by looking at the analytic structure of the Green's function, Fermi liquid versus the polaron, localized polarons, and you immediately kind of see this physics that the functions which you create, the expansion for the Green's function in terms of the coupling constant, they definitely face something which can be called divergent series. So you definitely have to resum them, and then you just create something which is polaron physics. But you have to go through the exercise of divergent series. So you cannot go without that. Yeah. So I'll probably stop here, but yes, you have two more slides just demonstrating how the Green's function of the polaron side looks like compared to the Fermi liquid it's totally good. I'll stop. That's just in case.
I have a very naive question. Can I see bipolarons as an incoherent charge density wave, something like that? Like, I don't know how to think about bipolarons. Is some kind of incoherent charge density wave, or?
The question is, okay, well, how to think of the bipolar as a variational state? We think about bipolarons literally as state. That's what was solved. Take two electrons, put them on one side, they cannot move. That's my wave function. Electron up and electron down on side 1. Electron up and electron down on side 2. Electron up and electron down on side 3, not moving. It's a well-defined state, well-defined wave function. So, okay, given this wave function, average your Hamiltonian with respect to this wave function. It's the estimate of energy for this wave function. The energy is lower. Now you will say, okay, I already know that this state wins. Now let's explore properties of the bipolaron state. First, solve for two electrons. What they actually do? Are they localized on one side, or actually they want to create a bound state which is extended? Can they move? What they do? Yes. You'll hear everything about this. Right now, I'm simply saying that every variational state wins. Once it wins, go and investigate what are the properties of the winning state with much higher fees. But I already know that, okay, I won. Unless you present something better. I would call it, in terms of superconductivity, this is buzzer system condensing using bipolar. That's what it's about. Yep, what density?
Say the state wind has lower energy, but is there some sense in which to get to this state, I have like exponentially low chance of fluctuating to that lower energy configuration? So I can, if I start here.
We kind of think this is probably first order, because the two states are so dissimilar. There is kind of not even good connection between the two, because in thermoliquid your mass is slightly normalized. The bipolar ions, just start doing the bipolar ions, they are exponentially heavy. So the two states are so different that I would think that, okay, we probably have a first order phase transition. If you actually do it manually, but this was never solved fully. Just to see this first order transition by doing full order diagrammatics. So you really see it from two completely different sides. You do thermoliquid and you can do port or bipolar. Then you compare them and you see, oh, there is mismatching energies at some point. But they just come as totally different terms. But once they cross, you say, okay, we probably have difference.
Follow-up question from myself. So you're saying that it's probably unlikely that you can use like that algorithms from your first lecture that you create that domain wall and then.
No, it's the first completely. No, if you ask me how for the first condition have, they happen through bubbles.
Nikolay.
Yeah.
Microphone.
When you ask me how the phase transitions happens in real life, yeah, they happen either by hysteresis or how it's called. Yeah, I know you the name just dropped for me. Sometimes you have first order phase transition, you see nothing. Just because the system is protected like kind of vacuum chamber. You go further in the parameters. You already know the other state is better in energy, but you cannot get there because it's exponentially protected by the domain walls. But ultimately, you get to the point when everything in your system becomes unstable, and then you just roll down. So this is stability point when you can start kind of more or less just collapse from one high energy state to the other one, which is much lower state, with some explosions. That's typical scenario. If it's thermodynamic limit, almost necessarily that's what will happen. Either your domain wall energy becomes, I know, relatively small and you can easily do it, but a little bit more and it will simply roll down. With hysteresis, if you are close enough to the transition. That's typical what people observe. Just like in magnetic systems, you have hysteresis for exactly the same reason. Sorry, if you grow the material, probably you don't have to worry. You will grow the right material right away because you do it at high temperature by cooling down.
I have a naive question. So like at strong coupling, the bipolar ions certainly wasn't, right? So is the novelty that weak coupling you're finding that?
At weak coupling, you'll start forming bipolar ions. Weak in terms of Migdal-Agterberg, but for the one in terms of the bare coupling. Sorry, in terms of the polaron definition. Yeah, let me show it again. In polaron community, people usually use this criterion. This criterion involves spectrum and the bandwidth. So this is some number which is related to microscopics of the physics, not the density of electron. In this sense, this kind of, if I take G squared divided by omega 0 squared and put W, the bandwidth, in denominator, this parameter is afford a unity when you start creating bipolar. That's what people see in the polaron community. But Migdal-Agterberg is using this parameter, which is involves density of states. That's the one which is responsible for the normalization of the spectrum or the Z factor. It doesn't involve the density of state. So this one is much smaller than one still. Can potentially be much smaller than one when you create unity here. Yeah.
And the Coulomb interaction state family.
Sorry?
And the Coulomb interaction.
Oh, yeah, sure. Coulomb interactions. This goes to my previous two lectures. Migdal-Agterberg theory is ignoring Coulomb interaction. It's just in using a pseudo potential to reduce lambda. Of course, Coulomb interactions are important because what will happen with Coulomb interactions? I don't know exactly because I cannot compute energy easily. I cannot easily compute energy of the Fermi liquid state if you have Coulomb interaction. My job was easy with electron phonon coupling. But once you say I have interacting electrons with Coulomb forces, computing energy now becomes a nightmare. No problem with bipolarons. I will simply say I will create up and down, not on the same side, maybe on the nearest neighbor sides. I'll play this game. Properties of bipolarons with Coulomb repulsion, we can solve it easily. I'll tell you properties of bipolarons with Coulomb repulsion easily. I can compute the energies easily, but I cannot compare to Fermi liquid with Coulomb interactions because this is the nightmare now. I just don't know how to do it with high accuracy, so I stay away. But typical discussion of Migdal-Ashberg does not involve Coulomb interactions. They just ignore it. Of course, they will change the picture totally.
First of all, for completeness, to complete the story, you probably have a slide about two-dimensional case, your results.
Two-dimensional, yes. Lambda Migdal-Ashberg saturates the constant. Yeah, this one.
I'm talking more, yeah, sure. I'm more talking about your results when density goes up and the normalized coupling goes.
Yeah. I already said that, well, okay, this phonon spectrum softening has a much stronger effect of lambda in 2D because it was like log in 3D, but first power in 2D. So yes, you can grow Migdal-Ashberg lambda well below, be above 1, can be 2 or even 3. Softening in 2D definitely will lead to much bigger. Yeah, I have graphs, but okay, I didn't show them.
But question about ability to do numerics. Before this happens, but close to this point, can you estimate the strength of vertical directions?
It's still small given the small adiabatic ratio. It's still omega d by divided by Fermi energy. It's a small parameter.
Well,
yeah, it's same Migdal theorem. Nothing changes.
Your phonon is dispersing phonon.
Yeah.
So the gap doesn't play that meaning as it had before. The most part of phonon is in dispersion.
Precisely.
So this is a question then.
Precisely. No, it doesn't change much, so it's still small. Well, because you see, part of the Migdal theorem was that frequency integration was limited by the phonon spectrum. It was already limited before. Now it will be limited probably even more. If you try to go to softer mode, you will limit your frequency integration even further.
But then play devil's advocate for a second. Somebody may say, in terms of results are great, in terms of logics, we know that at low density in 2 dimensions, for example, there is no Migdal theorem. Vortex corrections are comparable to self-energy corrections. So you are saying that there's no Migdal
if
theorem.
Fermi energy is much bigger than d by frequency,
You are still, but this limit is probably when Fermi energy even can be set to 0 in 2 dimensions.
No. I'm always doing Fermi energy much bigger than d by frequency.
What if Fermi energy goes to 0?
Then I go to the standard Polaron physics. I know all the answers. At this point, I say I can give you any answer you like. If Fermi energy is much smaller than d by frequency, I can solve it exactly.
Right, but then the question is this: this limit that you showed works even in a case when Fermi energy literally goes to 0.
It's a separate consideration. Yes, we can do it.
Yeah.
So far, everything I was discussing and all the plots I was showing, that's why you probably check that, well, this is not going all the way to 0. Why did I stop? Because I decided to take the first point in density to satisfy the condition that Fermi energy is bigger than d by frequency, at least by a factor of 2. Okay, not a great deal, but at this point, lambda itself is small. But then if I grow the density, of course, Fermi energies get better, but I don't go all the way to 0 for exactly this reason. I don't want to do density such that Fermi energy is less than d by frequency. Yeah, precisely for this reason. So just everything I discussed was standard Migdal-Ashberg. Suppose we have this parameter. Whoever is doing my homework, if you want to see maybe a bigger crowd or maybe the same, okay, please organize around to see who you are and just decide how you proceed.
We meet here in actually 12 minutes. Where presentation will be in the second part of both.
Not much, almost nothing.
Знаешь, лучше файл. У меня есть электроны с электронным электронным заданием. Просто по идее.
Because there are no electrons to solve important. They're delocalized. Yeah, because the electron density is small, phonons are local, vibrating within the atom.
Он будет сопресс из того, что будет фактор омега-9. И ты говоришь фактор. Если тебе не нужно верхний стрейк, что делать, то он еще ты как бы говоришь, что ты выиграл, ты победила. Да, там
Уравнение на собственное значение вы говорите, но оно скорее в пространстве, чем.
Ну да, потенциальное уравнение на пространство. Ну там, опять же, можно найти собственные функции легко, но дальше их нужно поставить внутрь собственной численности уравнения, да? И вот там уже будут все энергии. И оно, конечно, тоже пространственно зависит. Поэтому прибавочная функция. First order.
Oh, did you?
Наверное, синий проект.
Are you in line?
Okay, so it was keep with the work.
I thought there was.
I'm not answering, or I'm answering questions if you don't understand.
What's nothing?
It seems the same one.
If you just there's a like base. I think like I
All the questions about this.
or hunting it. Yeah, so it's sort of
Well, maybe it's first order.
No, Andre, yeah, I just thought that Andre and Kieran, oh, they just posted, nice. Because it wasn't posted like 5 minutes ago. So, extent, do they?
I think diagram diagrams are very bad at estimating predicted of estimation. Okay. You also replace conditions just in one. I don't know any study where people say, oh, I do diagram index and I predict the solution condition outside of the following. But good properties of one else. Good properties, another one, just see whether you can see it in other things, by doing the calculation. Diagrammatic is because well, we have different considerations. I'm a guy that for something. As long as we're evolving, once you change the thing, there are portables.
What goes that?
Let's say, well, you have this calculation,
Oh, I feel that's on foot.
I'm doing something that we should talk about just conductivity even smaller.
They said it's a volume.
All my terms are exact. Everything else we can go. If I think I think the transition actually could be fixed. There's the hierarchy, but that's what on frequency with condensation we will have to extend they want to extend it. Yeah, it is not going that's so beautiful statements. Different nothing like that. So. This is my dad. Any diagram.
So I thought for the same amount for, maybe it's the amount for. But the veggie one. I think that's three.
Yes, and if I, whatever you try to speak to, they're all, but let's do that. We don't actually that, so there's no, you're adding on top of this. God, this is an observation.
Yeah. You want to go first? Yeah.
Yeah, meeting later on. Yeah, но нормально, так сказать, я слушаю людей, но я делал когда там.
Comment, all right, via here, be on the whiteboard if you want to take a picture of it, otherwise it's on the website. And then the pickup is at Orium, the Church Street Garage. And the air quality alert. Might not want to go on the-
Okay, so we can start.
Hi, folks. Can you hear me in the back? Hi. So my name is Anant Rastogi. Today, I'll be presenting a poster on the superconducting diode effect. Now, this is a very common topic, and many folks have studied this both experimentally and theoretically. The basic premise that's needed for this superconducting diode effect to be seen is the breaking of both time reversal and inversion in crystalline systems. Now, what we have done in our work is to take this paradigm and apply it to the crystalline environment. When we do that, we do it by considering magnetic toroidal dipole and octopolar moments. Now, these are objects that break time reversal and inversion. Now, how this time reversal and inversion breaking interacts with the crystalline point group symmetries leads to basically this list of magnetic point groups, which will host the superconducting diode effect. And depending on the crystalline system, the nature of this superconducting diode effect would be different. So we have found evidence, we have found indications of magnetic point groups where essentially the superconducting diode effect will occur in the presence of a Lifshitz transition, which would lead to a pair density wave. We have also seen examples of materials where this is not required. So you will have uniform superconducting pairing, but still get a superconducting diode effect. We will also, thanks. We will also present some results for how this might occur or might be seen in cubic superconductors. So yeah, I'd be more than happy to talk to you and walk you through my poster. I hope to see you guys there. Thanks for listening.
Yeah, I'm going to.
Hi, I'm Ankun from Ariel University, Israel. So I will basically advertise my poster. I will start with a basic illustration. So here you see, it's a Dirac cone, hallmark of many quantum material. And most of us already know that this simple structure carries rich geometry, something like Berry connection, Berry curvature, quantum metric, and which all ties to band topology. And this weakly line represent interactions. They are associated with collective modes, which are inherently non-analytical function. That brings us to the right, a Riemann surface, basically complex analysis. Gauss-Bonnet theorem, Hairy-Ball theorem. You know, like in a funny way, you cannot comb a ball here in a smoothly. You will face one singularity. Maybe some of boys have two singularity in our hair. So that's it. My poster basically talk about why two of them cannot be separated out and how and why they are inextricably connected and why it is important in time resolved experiments. More details are on my posters if you are interested. That's it.
Yeah.
Okay, so my name is Ian. So I'm coming from the MFLab and I was there. So for my poster, I'm going to talk about the technique that we use, that we develop in our lab. So we use the ultra-fast pump probe spectroscopy to study the layer Nikolay system. In this case, it's the praseodymium nickel oxide. It's a tri-layer system, which people have seen that under the pressure, these nickels, praseodymium nickel oxide, I mean, for this system, the nickel oxide, they can achieve the TC of about 80 Kelvin, which is the boiling point of, well above the boiling point of the nitrogens. So for the poster, so we developed or we built the first ever high pressure pump probe system under the high pressure, low temperature, and high magnetic fields. So this figure is the transfer measurement measured by our colleagues. So at the ambient pressure, we see that there's the charge density wave. As we increase the pressure, the charge density wave got suppressed, and then the superconductivity start to emerge. And then in this experiment, we are trying to study the competing orders between the charge density wave and then the superconductivity orders. But unfortunately, we believe that for this praseodymium nickel oxide, the sample that we have is not about superconductivity. It's something we call preliminary superconductivity. That's why our experiment result is negative. But from the transfer measurement, the preliminary superconductivity is suspect to be about 6% to 10%. And then the gap size that we measure is about 27 milli electron volts. Thank you. And then, yeah, welcome to stop by for my poster. Thank you.
London.
Okay, hello everyone. My name is Chunhan Feng. I'm a postdoc at CCQ Flatiron Institute. In my poster, I would like to show you two of my recent work. One is in search of exotic pairing in the Hubbard model, many-body computation, and quantum gas spectroscopy. The pair density waves have attracted a lot of attention in both theory and experiment recently. It describes pairs with a finite momentum. Actually, it can be traced back to 1960s. The so-called FFLO state was proposed. The attractive Hubbard model provides us an opportunity. It can be simulated numerically and also can be realized in cold item experiments. So in the poster, I will show you several quantities we can narrow to capture such an exotic superconductivity state. And interestingly, we find even at a relatively high temperature, T equal to 1/3, we can already see some signatures of the exotic superconductivity, the FFLO state, and it's already within the experimental range. And another work I'd like to show you is also in collaboration with another cold item experiment group. And our collaborators successfully lowered the temperature of the system. And by comparing the experiment data with our simulation data, we find the temperature in the experiment is smaller or equal to 0.1. And this is several times smaller than the previous experiment. And at such a low temperature, more interesting physics could emerge. So if you are interested in these topics, please come to see my poster. Thank you.
Andreas.
My name is Andreas Feuerpfeil. I'm a second-year PhD student from the University of Würzburg in Germany. In my poster, I'll present the first experimental synthesis of ruthenium dioxide thin films with ultra-clean samples by controlled oxidation of ruthenium bulk crystal. We performed this study primarily because of some theoretical proposal of ultramagnetism in ruthenium dioxide thin films. However, by performing spin polarized and unpolarized STM measurements, we instead observed a long-range charge density wave order in these materials. This order coincides with both the Moiré substrate effect of the ruthenium bulk crystal as well as the Fermi surface nesting condition. By performing large-scale density matrix normalization group studies, we uncovered a resonance effect between these two, similar to a Fano resonance that explains the experimental peak observed in the density of states. If you have any more questions, I'm happy to discuss details with my poster. It's just to the left of this entrance to the hall. Thank you very much.
Nathan.
Hello, my name is Grayson, and I'll be talking about a recent work done with my advisor, Ili, from Johns Hopkins. So we're talking about an anisotropic Josephson coupling of D vectors rising in spin triplet superconductors. So as we learned from the first day of lectures, that for a spin triplet superconductor, it's described by a D vector, its pairing order parameter. And so if we consider the contribution to the free energy from a spatially varying superconducting pairing order parameter, it is in the discrete limit corresponds to Josephson coupling between multiple weakly connected superconducting grains. And so the first term can be thought of as a Heisenberg-like interaction term between these D vectors, which is more conventionally known as this stiffness. And it favors a collinear alignment of D vectors across superconducting grains. But what we show is that there's two additional terms that can arise, an analogy to a Dlazinski-Maria type interaction and also a gamma type interaction in classical spin systems, where this can favor non-collinear D vectors across superconducting grains. And from the Ambigalkar-Baratov formalism of the first order Jocelyn current, these three Jocelyn couplings can derive from microscopic tunneling across the grain barrier. And we showed this can arise on a system like in which itinerant electrons are coupled to localized non-collinear classical spins. We studied, for example, a 3 sublattice model. This is applicable to manganese germanium and also 4Hg phase of TAS2. We're now in the presence of these non-collinear frustrated spin moments. Is that the effective tunneling? Thank you. Effective tunneling now can give rise to each of these three terms: the Heisenberg-like, the DM-like, and gamma-type interactions. And we further show that when we have this like non-collinear d-vector texture, this can give rise to anomalous vortices, even in the absence of magnetic field, simply due to this d-vector texture, and can also give rise to a Josephson diode effect when the spin chirality of the underlying magnetic texture is non-vanishing. Thank you very much.
Anna?
Okay. Hi, my name is Anna, and the poster I'm going to present tomorrow is based on my recent work, where we studied time reversal wild semimetals in the excitonic phase. And we showed that in contrast to, for example, conventional excitonic insulators, where collective modes of the condensate of neutral excitons don't couple to the electric field. In wild semimetals, the electromagnetic field couples to the phase of the exciton condensate as a massive dynamical axion, which is a consequence of chiral anomaly and chiromagnetic effect in wild semimetals. And we also showed that it affects the electromagnetic response and leads to giant anisotropic polarizability and giant magnetic birefringence. So if you're interested, please come listen to my poster tomorrow. Thanks.
Hi, my name is Kathleen. I'm from the University of Toronto, and I'm going to be presenting a poster that is on a project I did on multipolar magnetism. So in mod insulators with strong spin orbit coupling, you can get an effective S greater than 1/2 spin moment. And this leads to local higher order multipolar moments, which can order. So this leads to kind of exotic phases in these materials. And so specifically, we looked at a spin 1 system, which has dipolar and quadrupolar moments. And these systems have strong single ion anisotropy. And so as you tune the anisotropy, you can go from a dipolar ordered antiferromagnet to a quadrupolar ordered phase. And so we used Monte Carlo and molecular dynamics simulations to study these systems. We coupled phonons to these systems, and we looked at the effect of driving these phonons. And so we got some cool results like effective magnetic fields and symmetry breaking, which leads to altering spin wave modes. So if you're interested in learning more, you can come talk to me tomorrow.
Hello everyone. I'm Jiglul Hassan. You can call me Joy. I'm from the University of Wisconsin-Madison. My advisor is Professor Alex Levchenko. You may have seen him here. My poster is on superconducting diode effect in helical superconductors. So people have thought about this before. As early as 1996, Victor Delstein first predicted this effect theoretically by considering the first Lipschitz invariant term, parity or term in the Ginsburg-Landau functional. Then later in 2010, Professor Dan Agterberg actually said, you can just gauge this term away, so you don't have any diode effect. But later on, around in 2020, people actually discovered experimentally the superconducting diode effect in those same systems where you have broken inversion and broken time reversal symmetries.
So how to explain this effect? So people tried using GL theory to explain this effect by considering next parity or term, next order parity or term, but then it was all wrong essentially. So only one of them was correct. Then we actually showed the generalities of this diode effect in our poster, and essentially what you have is even if you do correctly, if you consider the next order term microscopically, if you calculate those coefficients, you get a 0. So you get no diode effect. So essentially, we showed how to get around this by including interband pairing. And also disorder can also enhance this diode effect. We showed disorder, including non-magnetic disorder, actually enhances diode effect to some certain extent, and it can also induce some sign change in the diode effect. So if you're interested in this phenomenon, come talk to me. My poster is put up there. So towards the very end of the food cart. So thank you so much for listening.
Reruns.
Hello, everyone. My name is Kieran. I am a graduate student at Cornell. In my poster titled Frozonium, Freezing and Harmonicity in Flow-K Superconducting Circuits, I'm telling you a bit about some new theoretical methods in the field of driven superconducting qubits. So in this work, myself and collaborators propose a new type of Flow-K superconducting qubit we dub Frozonium, created by subjecting a inductively shunted Josephson junction to a high-frequency Flow-K drive. This work adds an interesting feature by way carefully tuning the Flow-K drive. We can cause the Frozonium to interpolate between two opposite effective Hamiltonians, a highly anharmonic Hamiltonian and a linear quantum harmonic oscillator. This is a bit surprising because anharmonicity is a key metric that defines the capabilities of superconducting qubits, where like some protocols requiring more harmonic behavior, like bosonic codes and certain types of quantum memory, and others relying on strong anharmonicity, like qubit operations and quantum gates. The ability for Frozonium to interpolate over a large range of anharmonicities is thus potentially exciting, as it would allow systems which require anharmonicity, systems that require harmonicity, to be unified into a single tunable architecture.
You have 30 seconds.
If any of that sounds interesting to you, feel free to stop by my poster, and I'm happy to tell you more. Thanks so much.
One G Lee.
Hi everyone, my name is Guangjie Li from Utah. I'm working with Professor Mengxin as a postdoc. So my poster will introduce this so-called cold joint orbit bossilization. That's the name. So basically what we want to do is we want to express the low energy excitations near the Fermi surface by some bosonic fields because these are particle-hole excitations. And in 1D, these particle excitations near the Fermi surface are described by the so-called Latinger liquid, which is quite successful in 1D. However, in 2D, there are many attempts, and recently people developed this cold joint orbit bossilization. And in my poster, I will first introduce you how to express the bossilized interactions. The bossilized Lagrangian under the weak magnetic field. And first with the single band case, which is simple to have some Latinger liquid around the surface. And there will be a Western innovation term that will give you the quantum oscillation. So our goal is to extend it to the multiband case, for example, the Rashba band or even the Exton insulator case. So, yeah. So if you are interested in the Bostonization in general, or you want to or you are interested in the cornell oscillation, please come to my poster. Thank you.
Tommy on the lane. Yes.
So, hello, I'm Tommy Molly from Aalto University of Finland, and I've been working on spin functional physics in relation to superconductivity. So, the goal of my project for quite some time has been to see how quantum geometry, understood as the geometry of Bloch states, affects the spin responses in various settings. So, there's two main lines of inquiry for that case. So, I've been considering an extension Hubble model for a parallel system, and then convert to Hubble U for multi system, and try to see what comes out of that. That's calculations, but for the time being, it's rather under construction that project. And because of an alpha project tool suffers. As a physical poster, but I'm eager to see if you have any questions at all. So it's great being here, and come and ask me if you're curious about speed functions and they need to play with quantum geometry. Thanks.
Natale Mastranga.
So, hello everyone, I'm Natale. I'm from University of Jyväskylä, Finland. And in my poster, I will talk about what just Professor Prokofiev told us about Migdal-Eliashberg theory. So, my system of interest is a flatband system. Flatband materials recently were under, say, list of scientists because they host this curious and rich, strongly correlated electron physics. And for this kind of systems, Migdal's theorem is normal valued. So in the treatment, we have to include all vertex corrections. And the goal of our work is to take into account these vertex corrections and try to compute relevant quantities that might be of interest. For example, the gap or the temperature. If you're interested, I'm not saying that's special. Thanks.
Ana Maria.
So hi everyone, my name is Ana Maria Ilic, and to start with something thought-provoking, and as we have a free afternoon, so if you don't see Mississippi River, so if you don't know this, if you look at a duck or any other object flowing with different speed in the water, they will always seem to make the same angle of about 39 degrees.
And take a microphone.
So any duck or ship flowing in the water with any speed seems to be always making the same wake of about 39 degrees angle. So think about it. Why is it? And my work has nothing to do about the duck. We think about waves as phonon, and what we think about is similar like what Professor Nikolay introduced today, is what if we have optical phonons, which are soft, and there is some acoustic phonons as well. what can happen if these two phonons belong to the same unit? And let's say you soften optical phonons even more, they cannot cross. So one case, like they will repel. And one extreme case, what can happen is that it will induce a dent in the acoustic phonon mode. And in principle, what can happen is in the material known as strontium titanium oxide, which is superconductor, is that this dent will become even softer than the how soft are optical phonons. And we are trying to see what effect in superconductivity this can play. So if you want to learn more about this or talk about the ducts, come to my post.
Siddhant, Mandra.
Hello, my name is Siddhant, and I'm working with Peter Hirschfeld in University of Florida. Most of you are familiar with the story of a magic angle in graphene. You undergo a phase transition and it becomes a superconductor. But what if I tell you that if you take two monolayer of cuprates, which are already D-wave superconductors, and start twisting them with respect to each other, then close to 45 degrees, you again see a phase transition. It goes from being a normal D-wave superconductor to a time reversal symmetry broken D plus ID superconductor. Now, there have been experiments which are done with this regard. Some experiments see the signature of the time reversal symmetry broken state, some don't. So most of my poster is dedicated to modeling these systems on square lattices, solving the BDG Hamiltonian, and looking at the full phase diagram with respect to the Hamiltonian parameters and seeing how the order parameter involves, where I have D state, where I have D plus ID state, and a lot more surprises which are in my poster. So please feel free to join me during the poster session. Thank you.
Kyung-Soo Park.
Hi, I am Jung-Soo Park, first-year grad school student here at the University of Minnesota. So this is some experimental work. So we have a superconductor, which is M through Al to C. It has chiral structure. So let's start with the molar to superconducting transition. So we have fixed the temperature and fixed applied magnetic field. And suppose we apply current like this, so that the induced magnetic field is pointing upward. Then the applied magnetic field and the induced magnetic field is parallel to each other, so they enhance. So now we have the state. We reverse the direction of current. The induced magnetic field is anti-parallel to the applied magnetic field. And the total magnetic field diminishes a little bit. Then we have superconducting state. So this drastic change in the state of material leads to non-reciprocal resistance. I welcome you to my poster.
Patrick, Vinay.
Hi, my name is Patrick Pinney. I'm a grad student at the University of Connecticut. I work with Pavel Volkov. My project is on the model that's been proposed for RCMO, excuse me. It is a quantum multiferroic with this phase diagram at low temperature. This is heat capacitance. And you see as you tune magnetic field, it enters this interesting phase, and there's also interesting capacitance response at this area. It's why it's a multiferroic. There's a closely related material without really a proposed model for it that is in this interesting phase and has this higher
field phase transition. And so what my poster is about is we're exploring the model for RCMO, which is this spin ladder system, and we're tuning the parameters and exploring the phase space and sort of seeing how can we get from RCMO to CCMO, and also what other interesting phases exist, what are the observables like, and we explore this with DMRG to find the ground state of the system. Yeah, please come to my poster if you'd like to hear more.
Alok Singh.
Hello, everyone. My name is Alok Singh, and I'm a graduate student at University of Rochester, working with my advisor, Andrew Jordan. And the results that I will be presenting in my poster are based on this work we did concerning abricose vortices in type 2 superconductors. So we use BDG equation to calculate the quasi-particle excitation spectrum near the abricose vortex core. And what we found was that it shows this really sharp asymmetry between particles and hole, especially near the vortex core, which is not immediately obvious why that happens, because the system seems asymmetric, naively speaking. So I would be happy to discuss like how do you come about that asymmetry. But it is interesting because for many years, people just thought that conventional superconductors do not show thermoelectric behavior at all because of the gap. You don't have low energy excitations. And also it's usually particle hole symmetric, so you don't see like thermoelectric behavior based off of that. But here near abricose vortices, we overcome both of these obstacles, and we show that we can see really large thermoelectric responses. Like in this linear response regime, this is the Seebeck coefficient. We see that at low temperatures, it's pretty like it's in the range of millivolts per Kelvin, which is higher, like which is much higher than normal metals. For normal metals in this temperature regime, it's
20 seconds.
Microvolts per Kelvin. So it's 3 orders of magnitude improvement over normal metals. And we also see really good figure of merit, which is a way to characterize an efficiency in the linear response regime. And I'm showing here also a nonlinear response of IV characteristic. From afar, it looks pretty reciprocal, pretty symmetric over both sides. But yeah, it also shows asymmetry in low voltage region. If you're interested, I would be happy to discuss more about this at the poster session. Thank you.
Read with me. Did I say it correctly? No, it's okay.
Hi, everyone. My name is Rory Sutcliffe. I'm a grad student of Arun Paramakanti at the University of Toronto. And today I'm going to tell you about my poster, which is about a project we worked on recently concerning the interplay of dynamics between phonons and multipoles in a multipolar Mott insulator. And so what we studied in this project is what is really a paradigmatic example of a multipolar Mott insulator in the osmate double perovskites. And these materials have a pseudospin 1/2 degree of freedom that lives on the sites of the FCC lattice, where 2 components of the pseudospin are quadrupoles and 1 is an octopole. And these, by symmetry, these quadrupoles can couple linearly to phonons. And so what we look at is by either pumping or driving these phonons, can we detect and control these multipolar magnetic orders in these systems. So if you're interested in that, you can come talk to me.
Andrews.
Hi, I'm Andreas Sabo from right now from ETH Zurich, but from Friday onwards, I'm at MPI in Stuttgart working with Laura Klassen. So my poster focuses, it's a work I've done with Alini Ramirez in Vienna, and it focuses on uranium ditelluride. which is a strong candidate for a spin triplet superconductor. And so we specifically look at the intertwining of the superconducting state with the charge density wave order that's been found on the surface of uranium ditelluride, but not in the bulk. And so the intertwining produces this pair density wave order that's only present on the surface. And the interesting part is that while the bulk superconducting order parameter is by symmetry restricted to the single component, the pair density wave inherits the multi-component nature of the CDW. And so this opens up new channels of potential symmetry breaking. Yeah, so we explore this direction and try to explain some experimental conundrums, and then also look into some subtleties and symmetry properties of the charge order. So if you're interested, come by. Thanks.
In person.
Hi, I'm Jefferson, and I like to tell you about my work done to detect time reversal symmetry breaking in twisted noble superconductors. And as Siddhant had mentioned earlier, in the vicinity of 45-degree twist, when you have the interface between two D-wave superconductors actually breaks time reversal symmetry. Now, because of the two-dimensional nature of this interface, most of the bulk probes that you would otherwise use to determine time reversal breaking actually doesn't work here. So I would like to take a phenomenological approach and look at this problem. And what we found, which will be the same, what we found is that by sweeping the system with an AC current, the first and the second order harmonic response of the system are actually necessary and sufficient for time reversal symmetry breaking. And more interestingly, we find that by in the non-perturbative regime, you can actually drive time reversal breaking in and out of the system. And if you're interested in any of these two topics, please come at my poster, which will be the first poster when you exit on the left when you exit the auditorium.
Hong Yu Yang.
Guys is okay. Hi everyone. My name is Hong Yu, and currently a postdoc at UCLA, working in Professor Ken Wang's lab. So, yeah, my postdoc will focus on this effect called superconductivity effect. Many of the previous speakers mentioned. So, in experiments, what we look at is really phenomenologically very simple. So, in a superconductor or a superconducting Josephson junction, we apply the certain bias in both in two opposite direction and see the critical current where the system leaving its superconducting state. And we found the critical current on both directions are different, and thus we can define a diode working range where the supercurrent will only flow in one direction but not the other. So when we look at the experiments and fundamentally we know to make this a phenomenon appear, we must break both inversion and time reversal symmetries. And because this deep link of this phenomena to the symmetry properties, as my title suggested, we can use this effect as a very sensitive symmetry probe, especially for time reversal symmetry breaking in a superconducting system. But also, we can also engineer these symmetry properties to enhance this device performance. So in the first case, the material we look into is this iron-based superconductor iron calculationite system, where it's been suggested that in this composition, tellurium and selenium close to 0.5. The band topology will emerge, and it is superconductor. So on top of that, among some of the scenarios that has been proposed, one possibility is that if we break time reversal symmetry, let's say locally, just by having some iron atoms on the surface, we can potentially generate Majorana bound states or Majorana zero mole locally at the iron atom, for example. So in that case, how do we probe this time reversal symmetry breaking really is happening in the superconducting state of this material? So in experiments, what I do was to use this 2D layered van der Waals materials, tear them apart and recombine them so that right at the interface of this top and bottom superconducting materials, we maintain a 4 angstrom van der Waals gap and also keep the atomically sharp interface so that the Josephson junction can appear. Okay, so final result is we see field-free superconductivity effect as a very strong evidence of time reversal symmetry breaking in this system. Also, I will tell you more about how we enhance the device performance in another work we did in this multi-Freud Josephson junction. Thank you.
Lei Cheng.
Hi everyone, my name is Lei Zhang. I'm from University of Michigan and the supervisor of Emmanuel Gao. And in my poster, I'm going to talk about sorry. So I'm going to talk about numerical analytic continuation technique that we recently developed. So what we do is so this is a process to sorry. Can you hear me clearly?
Yeah.
Okay, sorry. Yeah, so this is a process to extract the spectral information from mass-bar data. And what we do is, firstly, from the mass-bar data, we can get a controlled approximation of the transformed spectral moments. And then we use a minimal number of complex poles to fit these moments. And the key features of our method, methods are there are two main features. The first feature is that we found our method is systematically improvable. So that means we found that as the data precision increases, we find the recovered results become better and better. And the second key feature is that our method is generic. No matter whether your system is bosonic, fermionic, or diagonal of diagonal matrix valued, or sharp, smooth, or singular, it doesn't matter. We always found this feature. And on the right-hand side, I show some results from the real simulations. In this figure, we show the results from the continuous time quantum monocount simulation. And we found as the runtime increases, the recovery results we showing in the red dashed lines continuously improves. And in this final figure, we show the results we take the data from several consistent GW simulation and recover the band structure. And we found that even compared to this state-of-the-art method in the middle panel, our method on the right is still possible to have better resolution at higher frequencies. And also our method is very efficient. Basically, the middle panel takes about 800 CPU hours, and our method only takes about 2 minutes. And yeah, and I think that's all. If you are interested, you come to visit my poster. Thank you.
Okay. Hello, everyone. My name is Dmitry Zverevich. I'm a grad student at University of Wisconsin-Madison. And I'm gonna tell you the following story. As you might know, as you keep increasing the electron-electron interactions, the electron system might crystallize, forming what is known as a Wigner crystal. But the densities required for that crystallization in the monolayer case are very low. But if you introduce a second layer to the system at intermediate distances between the layers, the crystal might be stable up to higher densities. And that's not all, because like this electron crystal will also undergo a set of structural phase transitions and more interesting stuff. So having that in mind, we studied magnetism in such a system of like dilute bilayer Wigner crystal. So if you're interested in that, come check it out, ask me questions. Yeah, we'll be happy to answer them. Thank you.
That's all. Thank you very much.
Thanks.
So I guess everyone knows what to do next. The bus will leave promptly at 2 p.m. from Church Street Circle, and ask any local person. It'll take 2 minutes maximum to walk there. And let's do that.